Okay, good morning. Welcome back to the second day of our Combustion Institute Summer School here at KAUST. We're going to continue our lectures in fundamentals of flames, following the very insightful lectures yesterday by Professor Maruta on studying flames and flame dynamics using experimental methods. Today we're going to have our very own Professor Hong Im. Professor Hong has obtained his PhD from Princeton University and then went to work at Stanford Center for Turbulence, and after that in Sandia National Lab, and eventually became a full professor at the University of Michigan in the Department of Mechanical Engineering. He joined us at KAUST about more than 5 years ago, again as a full professor of mechanical engineering and working in the Clean Combustion Research Center, leading all our activities in combustion simulations. So he has many years of experience in high-fidelity computations, high-performance computing, utilizing methods like DNS, LES to study turbulence chemistry interactions in very complex devices. Today's lecture, I'm sure it's going to be a good combination of fundamental flame theory together with applications of these theories in practical devices. So please welcome Professor Hong.
Thank you, Manny. Can you hear me? Well, okay. Good morning. Thank you for coming for all the hours of the weekday. It's my great pleasure and honor to really give a lecture to this audience and people from all over the world. And I'm really delighted that hopefully you'll make your times worth. So thank you, Kaoru Maruta, for excellent lecture yesterday. It's going to be a tough act to follow. But the lecture today will be more on kind of complementing what he presented. He gave a lot of excellent laboratory examples to talk about what kind of science questions we are dealing with in combustion research. Today, main focus is more on theoretical studies and modeling aspects of the similar fundamental, as well as eventually I'll have a chance to introduce more on the application aspects. Before I start, I'd like to acknowledge the excellent group members of my laboratory. We have about more than a dozen, about 15 members, led by my research scientist, Francisco. I am going to use laser pointer would be better, right, for the online audience. And I just found out I can have a blue laser here, which is not commercially available at the moment. So this is a high tech. All right, so I have excellent group of people. I'm also proud to say that my group alone represents 10 countries. So this really attests to the extreme diversity that KAUST really enjoys. And it's been a great ride. I've been here for 5 years, just working with this excellent group of people from all over the world. It has been definitely a privilege. Again, I would like to also thank all the collaborators, again, outstanding colleagues at KAUST, as well as my other various types of collaboration activities going on. They all directly or indirectly contribute to some of the materials that I'll be presenting. And last but not least, I would like to thank the financial sponsorship by the Institute, CCRC, and my research funding coming from KAUST and Saudi Aramco. So the outline, I would like to give 2 parts. I have 2 presentation material, each wrapped up by some summary slide. So I would like to take the halftime break. I have roughly 3 hours. Usually that's our teaching schedule. We have 1.5 hour class. So I'll try to have about 80-minute lecture, first part, and have some 20-minute break, and I'll come back to finish off the rest. So the first half will be mainly focusing on basics of the theoretical aspects. Again, my PhD work has all been without computers, a minimal amount of computer calculations. I did a lot of these theory description. And in my opinion, those aspects are unfortunately going away. Not too many people do PhD work out of this kind of analytical study. So I would like to hopefully give you a little bit of a glimpse of these insights we have gained over the classical theory of combustion. And then I will give you some basics of the modeling aspects. What kind of calculations are done behind the black box that you run every day? These days, it's a Cantarized kind of routine calculation for every graduate students. But maybe quite a few of you may quite not have exactly thought about what is going on inside the box. So I will give some brief overview of that, and I will review some of the canonical flames. Again, my point is Professor Maruta gave good examples of how those experiments are run, what kind of things are investigated. I'll try to give an overview of how those things are being computed and modeled, what are the mathematical and computational issues related to that. And after the break, I will talk about mostly focusing on turbulent combustion. Some regime is always important, and I will start with that. And then the remaining part is basically divided into three usual things: DNS, LES, and RANS. And I will finish up with some application example. Well, so it was not as easy to prepare all these 3-hour compact lectures. I ended up taking out a lot of advanced material and application example and so on. So because I just wanted to focus on a few things. In my opinion, always 1-hour lecture, if you can get a couple of neat points out of the lecture, that's something that you didn't quite think about, I think that would be a successful lecture. So that's kind of my spirit of the following 3 hours. So let's see how it goes. All right, so just to motivate the audience, I guess many of you are coming from various backgrounds in industry and academia. Well, why are we still working on combustion? I personally, firmly, not just because I'm biased, I'm doing combustion research, but I think if you put all the scientific thoughts, rational thoughts, it's pretty clear that the combustion of some kind of fuel, it doesn't have to be fossil fuel, is going to be important. And it will continue to be a viable technology toward the sustainable energy portfolio. So, but people still try to push the combustion devices. I'm giving some few photos from the online search. So we want to improve combustion systems in terms of efficiency and emission performance. And so we already got some good idea about how we can achieve that. And some of the keywords include high pressure and lean burn, which is often combined with the mild combustion that Professor Maruta talked about. You want to have a preheated, extremely lean condition to reduce the pollutants. And a lot of as you are pushing the combustion condition to this extreme condition, oftentimes combustion happens in neither non-premixed nor premixed. Sometimes it's dominated by ignition mode. So it's all sorts of complex mixed mode combustion is happening. And I'll give you some background about what is a modeling challenge in dealing with those kind of systems. Another important aspect we are exploring now is fuel flexibility inside any of these engines. Well, for example, in an internal combustion engine, we want to have an engine that can burn any fuel, and that would be the future. And this has a tremendous impact in light with some of the new arising concepts like solar fuel. So we can manufacture fuel out of the carbon neutral sources. So again, those are kind of a lot of issues. And more recently, we are also paying a lot of attention into new development of the supercritical CO2 as a working medium, as a power cycle, as exemplified in this EcoGen device. So again, the point I'm trying to make is that all these are new realm of the combustion behavior. Unfortunately, is done at the quite complex situation. High pressure, highly turbulent, and extremely boosted, all sorts of things. So it's something that has not been quite explored in our conventional combustion system studies. So, and also it is going to be a lot harder to model and predict and measure because of the scale disparity will be large and so on. So that's the main kind of task that all the young generation ought to do for the next 10, 20, 30 years to come. We want to further advance our modeling and the experimental capabilities so that we can design toward the future combustion devices. So, well, you have seen the big combustion rig, the 2-story tall. This is really one of our flagship device, system, run by these outstanding scholars at the CCRC. So we have been conducting some of these the laser diagnostic measurement of these what seemingly kind of benign turbulent flames, but when you actually look at it by cliff image of the instantaneous images, you find a lot of complex structures, and that becomes more and more complicated. And that is something we want to investigate. So you can see there's some intense burning region, and there are other spots that is relatively weak, and sometimes it's considered to be partially extinguished. So just understand, gives you an idea about understanding this extreme turbulent combustion and flames. Has to deal with a lot of complex aspects about burning, extinction, reignition, and the associated pollutant formation phenomena. So, well, let me jump to the punchline of my 3-hour lecture. If you get bored toward the end, just hopefully I will leave this one as a take-home message. So I hope I would like to give some appreciation and ode to classical theory, which actually opened a lot of avenues toward the subsequent detailed combustion studies. Why theory? Because it gives us a clear idea about what is the important physical processes in a non-dimensional fashion so that we can clearly derive some nice scaling relation. And to me, I think from all engineering purposes, that's everything. And all the detail, you can fit it, the curve can be fit, you can do the rest. But what is most important thing is the leading order behavior, and that was done well by the historical asymptotic theory. We deal with a lot of non-dimensional parameters in combustion system. So there are 2 major parameters, especially in combustion. When the fluid dynamics, we talked about Reynolds number, Prandtl number, also, and so on. In the combustion system, there are 2 most important parameters. First one is the Damkohler number, which has many different definitions. It's formally defined as a ratio of the characteristic reaction rate to the characteristic flow rate. Or you can inverse that, and you can talk about characteristic flow time over characteristic reaction time. So that large Damkohler number means you have more intense chemical reaction compared to the flow time, flow rate, and vice versa. The other important parameter is a Zeldovich number, which is essentially a non-dimensional activation energy. There are a slight variety of the definition of that, but meaning should be clear. What I'm going to point out is that in the typical combustion system that we are dealing with, these 2 Damkohler number and Zeldovich numbers are typically very large. And that is the main reason why the problems are difficult, because it poses a lot of strong nonlinearity in the problem. All these nonlinear problems are harder to analyze and predict. And also, today's combustion research, we are dealing with many complex chemical reaction systems. And for those systems, sometimes it's not easy to identify a specific chemical time scale, because we are dealing with hundreds, if not thousands, of the chemical reaction steps that spans a wide spectrum of time scale. And oftentimes, these different time scales dominate at different combustion regimes, so that's what makes the things a lot more exciting and complicated. So what's the effect of the large Damkohler number and large Zeldovich number? Just to show you a kind of a graphical image of that. Well, I have to give an example of 2 different scenarios. One is a non-premixed flame, and the other is a premixed flame. I will revisit this definition of the mixture fraction, but this is a kind of a non-dimensional coordinate that sets apart from fuel to oxidizer stream. And when the flame is established in between, called in the stoichiometric location, and temperature reaches the typical adiabatic flame temperature. Damkohler number being the chemical reactivity, as the Damkohler number goes very large, then the reaction becomes intense. So in the non-premixed flame, the flame can burn as much as you can bring your fuel and oxidizer together. So in the infinite Damkohler number limit, you will see the flame reaches the maximum possible value. But as the Damkohler number decreases in a finite rate, chemistry takes place, and the maximum temperature is not as high. And as a result, there are some kind of, not all the reactants are completely burned, and they start leaking. So that's the fundamental thing. Once you start doing that, and this is fed back into activation energy, into reaction rate, and if you have a significant amount of drop, then flame cannot sustain itself, and then extinction happens. The Damkohler number, as I was showing here earlier, it usually scales with this chi. Chi is defined as a mixture, the scalar dissipation rate. It is a function of a gradient of the mixture fraction. We will get back to that in a moment. Zeldovich number, activation energy. What is the activation energy role? Activation energy is what's inside your exponential term of the chemical reaction rate. Activation energy decides how reactions are focused near the maximum temperature range. So as you can see here, as the Zeldovich number increases, if I scale my reactivity, normalized by its maximum possible, span over the temperature range from 0 to the maximum temperature, you will see because of the nonlinearity, reactions are more focused on maximum temperature region. But that focusing gets more and more severe as the activation energy increases. And there's something called the flame sheet limit. When actually the activation energy goes to infinity, then reaction only occurs at the infinitely thin sheet, which is also called Burke-Schumann limit. And all the rest of the region is a non-reactive. So that was actually an important foundation of simplifying the description of the non-premixed combustion. In the non-premixed flames, therefore, infinite activation energy, flame sheet limit, is a perfectly valid mathematical asymptotic limit. And it is important to remember. So, which is also, we also call it, non-premixed flame, is diffusion control combustion. So flame sits there. I have a burning factory, burner, and just bring as much as you want. I'll burn it instantly. And that's the main idea. So that's the main feature about non-premixed combustion. Premixed flames, I want to remind you that it's different. So what is the effect of Damkohler number? Well, it's not so simple, actually, as there have been a history of research, including Professor Law, who was my former advisor. He did a lot of this measurement to find out, actually, how do we change the Damkohler number, typically due by the strain rate. And so he did the counterflow premixed flame measurement and tried to measure the flame thickness in terms of thermal temperature profile at various scalar dissipation rates, strain rates, where the maximum value shown here is close to extinction limit. And surprisingly, you could overlap these four curves like that, and they don't change. So it's quite counterintuitive somewhat, but that's kind of how premixed flame behaves. So I just want to take home message is that the premixed and non-premixed flame, they behave differently in the way they respond to the fluid dynamics. What is the effect of Zeldovich number? This is also kind of foundation of the asymptotic method, asymptotic theory. Again, like I said, reaction, because of this exponential nonlinearity, large activation energy, typical Zeldovich number of the typical hydrocarbon system is order of magnitude larger, about 10. And which means that the reaction layer, even if the temperature profile is roughly approximated like linear function like that, reaction is focused within very thin layer. Again, it's very important. The reaction source term in the governing equation is always a pain. You have to deal with that. If you don't have to deal with it for 90% of the zones, that makes our life a whole lot easier. So this is a concept about this asymptotic flame structure. So there is the preheat zone thickness is governed by convection diffusion. but reaction is only focused within those order of magnitude thin layer. However, because the nature of the premixed flame, in summary, is always a reaction and transport balance. There is a perfectly one-to-one match to establish premixed combustion. So in that sense, infinite Zeldovich number limit, like in the flame sheet limit in non-premixed flame, is not valid, even conceptually. You cannot imagine premixed flame that has an infinite chemical reaction rate. Chemical reaction rate is the one that dictates the flame speed, and it has to be finite always. It's a very important concept to remember in understanding combustion dynamics. All right, so again, let me revisit S-curve. Again, I think S-curve is really important for every combustion practitioner. And let me start to spend some more time on that. We have already discussed it. What is the S-curve behavior? This is what we call a phase diagram. So each point along this S-curve line is a steady solution of a combustion system. I have input parameter. So Damkohler number, like I said, is an important system parameter. It determines within my reaction system, in my burner, or within the flame, whatever, the ratio between two characteristic time scale. And each of those time scales, you can find out the actual steady solution for the flame temperature you can get. A large Damkohler number is an intense reaction, so you are approaching equilibrium. If Damkohler number is way too low, then this is not going to burn, it's frozen. And then as you increase the Damkohler number of the reactivity of the frozen flame, it jumps up to the flame mode. And there is a hysteresis, and that's what is signified by this S-curve. What's causing this nonlinearity? Why do we have this non-monotonic response? Anyone? What's causing it? Do we have a ball? Bob, can you control that? So what's causing this nonlinearity? This is a typical signature of a nonlinear system. The answer is already written on the board. It is an action of nonlinearity associated with activation energy. Chemical reaction is exponential function, and the larger the activation energy, the more severe this nonlinearity gets. So as you can, actually you can do analyze a system and find out as the Zeldovich number gets smaller and smaller, and actually from frozen to equilibrium limit can be done in monotonic way. So there is no drastic hysteresis phenomena such as ignition or extinction, but instead it's just kind of a slow transition, continuous transition from frozen to fully burning state. Our life would be a whole lot easier because everything is one-to-one, but unfortunately, real combustion system, this Zeldovich number is large, and therefore we have to deal with this nonlinearity. And we also know that this middle branch we talked about yesterday is unstable. How do I know this is unstable? Well, that's the theoreticians do the stability analysis. You start from the base solution somewhere on this line and try to perturb it and see where that perturbation goes. Conceptually, it's easy to understand. As you move around on this line, your Damkohler number goes up. I'm supposed to enhance the reactivity, but instead it's going down. Temperature goes down. So I cannot stay here. Any perturbation will push me out of this branch and eventually go into the lower branch or upper branch. So that's the general description of the S-curve. Now, one final point I would like to note is all this S-curve gives us information about steady system response. The system will sit there forever. If I have a premixed gas of hydrogen and air kept at the room temperature in a box, it'll stay forever like that. It'll never ignite. However, if I ignite it, and you'll have a continuous flow of that like a burner, and then you will stay burning forever. So these are the steady diagram. These are steady, I put it in a capital. It's a steady response. It does not, however, this S-curve does not tell us about the transient dynamics. And a lot of times in a practical system, we want to understand those transient response. So let me redraw the S-curve here. Once again, repeat of that. So you have an ignition branch, extinction. So you have a flame burning, fully burning, and frozen branch. So imagine my system has certain Damkohler number around this region, and I have steady solution right here. It will never ignite. Again, it'll stay forever. So in order for the system to be ignitable, I'll have to push the system beyond this ignition turning point. Likewise, if I'm here, I have already fully established a flame. It's a steady flame solution. I am never going to be able to extinguish it until my extinction Damkohler number, DAQ, is reached and further below. So from that point of view, I call this is the Damkohler number. It's the Damkohler number that is a system parameter that we have control over in a combustion system. So this is the ignitable region, and that's the extinguishable region. So you keep in mind, if you are in between, you either have a burning or non-burning solution, okay? And if you are talking about the ignition, extinction, and reignition phenomena, we are somehow, temporarily, you have a local swing of the strain rate, or Damkohler number, to move the system out of this S-curve into this region. And then you have to bring it back to this in order to be able to reignite it. Otherwise, it'll be gone in full extinction. In terms of dynamics, I can overlay the dynamics picture. How long would it take then to ignite? The ignition delay time will depend, of course, on the Damkohler number. Right? The larger Damkohler number will be more reactive. I'll ignite faster. So imagine like a homogeneous reacting system where ignition delay time of that system is plotted as a function of Damkohler number. It'll be very short, and it'll approach, keep increasing in an exponential manner because of the chemical non-linearity. So this is how it's going to look like. So this is a red axis is a time axis, ignition delay time of that system as a function of Damkohler number as it approaches ignition limit. And at that exact ignition point is a kind of a mathematical singularity. It'll go to infinity. Same thing can be expected. Well, people don't talk about it much, but if you want to actually capture how long it takes when the flame actually goes away, and then you have to bring the system into here, depending on the corresponding Damkohler number of the system, the time for it to take to extinguish will be faster and faster if you bring it further down into the lower Damkohler number. So that's the general understanding of how to look at this S-curve. I think it's important to realize the two different pictures about steady and unsteady. If you are dealing with some practical engineering threshold, like ignitability, will it be ignitable? That's sometimes all that matters. We're not really concerned about time scale of how it, once it explodes, that's gone, it's accident. So steady curve still gives us a meaningful information. But on the other hand, if you are designing an engine where I have this much time window to burn everything, then how quickly it can ignite matters a lot. So you need to design the combustion system so that you fall your Damkohler number during that crank angle degrees to fall around here instead of here. And that's a kind of another fundamental information we want to look at. So counterflow flame has been discussed a lot. Again, some people who haven't thought much about it may wonder why do we even do that, right? How does it relate to engines and jet, the combustor and the gas turbines? Because, again, everything falls back onto this Damkohler S-curve. So this system, every system, no matter how complex you have, locally the chemical system is a balance between reaction and residence time, which is given by the fluid dynamics and transport. And that ratio between the two, Damkohler number, is the single most important thing to determine your state of the combustion. And so counterflow is an excellent example in a way that, well, other than obvious fact that you can reduce the mathematics into 1D system, which is a lot easy to compute, but I would like to emphasize that you can independently control chemical reactivity. You have a question there? Can you throw the microphone?
On the previous chart, you are showing the Damkohler number, but in a real system, the Damkohler number will be sort of a range of Damkohler number because there are many, many reactions.
Absolutely.
And all that. So how does a simplified version like this will help us understand the real scenario? And yeah, that's my question, yeah.
Yes, so I will show you the example of what happens to this S-curve when there are more than one time scales. And you can create multiple reaction turning point. But yeah, so it is actually important. The turning point is important phenomena of interest. And each turning point is driven by a certain chemical reaction pathways. And indeed, mathematical analysis will tell us that. So that way, instead of throwing in hundreds of reaction steps, I will be able to identify which other highly nonlinear chemical reaction steps that is responsible for that turning point.
Thank you.
I think that will be the important information from all practical point of view. And I will show you an example where there are more than one turning point, and which is a good example is the NTC chemistry. All right, so the counterflow system is great in that the Damkohler number, the denominator and numerator can be controlled independently. How do I adjust the numerator chemistry? I change the mixture composition, and then heat up the upstream gases and so on. You can adjust that without affecting hydrodynamics. I can fix the chemistry and change the denominator of hydrodynamics by changing the velocity. So it is really, if you think about this, is a one-of-a-kind, really clever device that can allow us to explore whole map of this Damkohler number space. And well, I know everyone have seen counterflow flame studies and papers, plenty of them. But I just hope you understand why people for the past many decades have been beating this subject to death. And there is a reason for that. Well, so let me go further back. This is a 1974 paper. Who reads this 50-year-old paper? But actually, there's a lot of wisdom. And when I studied my master program, I was first time studying combustion. And during the winter time, before I start actual regular semester, I derived this paper from line by line for all equations. And we spent about a few months of study of this single paper. But there's a lot of episode behind this because Amabile Linian is a well-respected theoretician, a good friend of Foreman Williams. And it was actually Foreman Williams. He put it inside his drawer for many years. He derived everything without publishing it. And it was Foreman Williams who actually forced him to publish and helped out actually the manuscript. Anyway, so this is one of the seminal work that introduced the large activation energy asymptotics and talking about all that. So, well, what I'm trying to point out is this counterflow system can be analyzed very easily through an analytical tool. And this is a configuration we have. It's the doubly infinite domain. You have fuel coming from one side and oxidizer coming from the other, forming a Hemans flow axisymmetric geometry. And then further, you can simplify chemical reaction by one single step. And furthermore, we assume constant density. Wow, how ridiculous is that? Combustion, how can you assume constant density? Well, for the intent and purposes, actually it's not a bad assumption because what I want to know is the interaction between fluid chemistry and fluid dynamics. So once you assume that, and steady balance equation is like that, and then one-dimensional approximation based on similarity. Again, I don't want to dwell on detailed derivation, but I just want you to appreciate how you can simplify and reduce the mathematical problems into a amenable system. And unfortunately, we don't do this anymore. And all the graduate students, first day in the lab, they are taken over the converged code, and they run multi-D simulation, and you get massive amount of data, and what do you get in the end? And that's something to really think about. So mathematical reduction can be further done, and by some clever coordinate mapping, actually, this complex, the counterflow system equation is reduced into simple linear ordinary differential equation with reaction term. And that's the kind of a beauty of this analysis. And he categorized all these important regimes that was highlighted here. Frozen, partial burning is the middle branch, and premixed, near equilibrium branch, everything in one paper. So the rest is a detail, and I can skip that. So then this paved the way to identifying different types of combustion regimes you can anticipate depending on the boundary condition. And one of the important, interesting aspects that this paper revealed was that actually even if you have this perfectly non-premixed system between fuel and oxidizer stream, counterflow, depending on the boundary condition, if one side is much hotter, for example, then you can actually have enough of the leakage of one reactant to the other side, then it looks like a premixed flame structure. So this is commonly called the premixed flame regime of Linian's analysis, and people had many of the follow-up studies. I don't want to dwell onto those mathematical and analytical subtlety, but basically the point is that this asymptotic formula has been derived to cover the fully premixed flame combustion system. And at the end, it was an ignition extinction turning point in this steady system that has been analyzed, and the extinction Damkohler number. Again, this is another beauty of the analytical study. The reduced Damkohler number is a non-dimensional number that has everything in it, the boundary condition and chemical reaction rate constants, everything is in there. Of course, it's a one-step chemistry model. So if you want to extend it into detailed chemistry, well, there's a limitation. But as we have seen many times, actually if you run optive calculation, I will show you mechanics behind it, you do reproduce this perfect turning point behavior using GRI mech running on optive flames. So there's clearly one dominant reaction step, maybe not necessarily one step, but it's some combination of one chemical modes that is responsible for this driving the system dynamics into nonlinearity. And it's this nonlinear behavior of turning point is the most critical, important aspects about combustion study. So ignition analysis has been done here. Again, for example, this is a reproduction of the lower branch turning point of the S-curve we discussed earlier. And now you may want to, I would like to, you to appreciate this actually turning point, like I said earlier, becomes monotonic as this is a different curve generated by different parameter called beta. Beta is the temperature ratio. And actually, interestingly, when the beta gets larger than 1, the order of 1 and larger, actually the combustion response becomes monotonic, which is what I explained earlier. Guess what happens? We are talking about the situation where fuel and oxidizer opposite stream, but one side, air side, temperature is hotter than adiabatic flame temperature. Under that scenario, actually, there's no extinction, or ignition for that matter. It just, everything just sweeps through in a continuous reactor system. So you can reach from frozen to equilibrium solution in a gradual, non-monotonic response. And that's a kind of, it makes a lot of sense. So theory really sharpens your mind, and it really nails down essence of the physical system. And whoever is doing laser diagnostics or DNS, LES, I think this kind of concept should be clearly kept in mind. So this was about steady analysis. And then once I'm in that region around here to be ignitable, how do I analyze that system? And that involves the unsteady equation. As you can see, all these equations are steady version. Now you can analyze. This is one simple example of an adiabatic system with homogeneous reactant mixture. So temperature evolution of the system can be driven by reaction source term. You can add extra heat loss term, whatever, and this one doesn't even have a transport. If you want to deal with this spatial transport non-uniformity, then you throw in those terms here, and you get full Navier-Stokes equation. So this is a simplified version of the homogeneous reactor, and it'll go over time. And that, well, skipping all these analytical detail, but this is such an easy, simple system you can solve by hand. And this is a part of the asymptotic theory, the expansion. So what we are essentially doing is the temperature start from frozen temperature, perturb it by small parameter, epsilon, which is inverse of the activation energy. Then this data, we watch how this data evolve over time. The main purpose of analytical study of doing small parameter expansion is so that you can linearize the system. And that answer comes out to be a very nice analytical closed form solution. For the theta, like I said, this is a temperature perturbation from the frozen solution. It blows up over time at 1 in the normalized time scale. What is that T tilde? Well, if you want to determine ignition delay time, everything is in there. So you just plug it in, and you get the ignition delay time in physical seconds. So that's the kind of general theory behind it. And that has been well established. I hope you can have all these picture about, again, the main point is a distinction between steady and unsteady dynamics of the combustion system. I think that's very important to know. One more, this subject was also covered yesterday. One more thing that one triumph out of this asymptotic theoretical work was intrinsic flame instability. We talked, this is also known as commonly called the Lewis number effect, but there's more to the story. So this is a very, there's a long history behind, dated from 1930s and 40s all the way to 1970s and 80s. The main gist of it is that we have identified two major mechanisms that the flame, without hydrodynamic perturbation, flame itself, initially perfectly flat, can develop some wrinkled structure. And there are two distinct, completely different mechanisms that cause that. One is called hydrodynamic, called the Darius-Landau model, and the other one is a diffusive-thermal instability. And those are manifested in different length scale, so you can actually easily tell inside the laboratory. So this is an example. For a lean hydrogen air flame, you see these are smaller scale wrinkles, which is a sign of a diffusive thermal instability. And large scale wrinkle, even if this is a diffusive thermal, is stable, as a flame, spherical flame grows, you find some kind of this crest region, and which is a sign of hydrodynamic instability. So I don't want to get into too much details of the mathematical model, but this was done in Darius-Landau model, 1945. Actually, Darius did it in 1939, and Landau did it in 1945. Actually, I always joke about it. If today somebody published a paper 6 years after, then you'll be sued for plagiarism. But that, those good old days, you can still get equal credit in the span of 6 years. So the Darius-Landau model shrinks the entire flame structure into thin sheet. Again, so flame structure has no meaning, and every flame front is moving in constant velocity. And what we are watching is, so the main objective of this kind of theoretical analysis is when the base solution of the flame is flat and you try to perturb it in this method of normal modes, that's what we call. So some wave number, you can determine the size of the wrinkle and see how that perturbation amplitude, F, grows over time. And that temporal information is given by omega, shown here, as if omega is positive, and it's going to be exponentially growing. So ultimate goal of this type of linear stability analysis to find the dispersion relation, which is an analytical relation between omega and K, and then you want to make sure this omega stays negative to remain stable. So that's the first thing they did. And they found out the nice dispersion relation, which is given as a function of mainly Q. Q is the heat release ratio, the ratio between temperature between upstream and downstream. And the larger Q means the higher heat release, larger density jump. And they found out omega, real value of omega, is positive for all wave numbers. And that slope gets steeper and steeper with the higher Q. So the conclusion was that it's absolutely unconditionally unstable. You can't possibly have flat flame in the lab. The physical explanation of the mechanism is rather simple. Actually, you can, this is a nice diagram that you can kink the flame front like that. We're talking about constant flame velocity everywhere, normal to itself. And then it forms streamline deflects like that. So this is a modified stream tube. Stream tube means the flow rate is the same. So what it means is that along this streamline, the upcoming velocity slows down, and it accelerates here. So if it slows down, flame speed is the same, so meaning that flame speed is faster than upcoming speed. So this flame will keep going without stopping. And likewise, this flame will slow down, continue to go forever. So there's no way to stop this. And that's the mechanism. Completely hydrodynamics, it has nothing to do with the flame structure. And this is like a D'Alembert paradox. Well, I do observe flat flame in the lab. How come? Well, now we know why it is happening. And at that time, it was like a paradox. And it was a Markstein in 1950s who come up with, so main assumption flaw was that the flame speed is constant. And so in order for the flame to be stable, you have to allow that flame speed has to be variable. And in fact, Markstein heuristically came up with the idea this flame speed is a function of curvature. And this is the origin of the Markstein length. And that mu here is a coefficient, which is should be in the unit of a length unit, and that is called the Markstein length. Subsequently, Sivashinsky, another greatest mind in combustion theory, in 1970s, he conducted this asymptotic analysis called the diffusive-thermal model, which means now we understood Markstein proved that it actually can stabilize it. And let's examine, because the flame speed changes, and now we need to look inside the flame structure. So that's what he did. And this is asymptotic structure I described earlier. So we have order 1 hydrodynamic scale, and order delta, which is much smaller, the preheat zone. And then within that, another scale of the Zeldovich number beta, 1/10 of the layer is a chemically reacting zone. So he conducted asymptotic analysis across mainly within this layer and derived the same method of normal modes. He derived this new dispersion relation. This time, this dispersion relation, omega versus K, is a function relation here. And important parameter here is L, which is found to be the departure of the Lewis number with respect to unity. And this is well-known diffusive-thermal Lewis number instability. So we found out that the Lewis number greater than 1, you can stabilize a flame front. And as Lewis number gets smaller and smaller, actually, flame can be unstable. And this is what's responsible for wrinkle structure we saw here. So everything is clearly identified. And the mechanism here is well understood now. When you kink the flame front, so it is Lewis number is a ratio between mass and heat. On top is alpha is a thermal diffusivity, D is a mass diffusivity. The ratio determines which one is more dominant. And when you have a convex flame front moving that way, heat is defocusing, and mass, the fuel coming into the flame, is focusing. If Lewis number was 1, those two effects offset each other, no effect. But if Lewis number is less than 1, then mass wins, So this flame front gets speed up faster, and therefore the instability grows. So it's a simple heuristic mechanism. So those are the two aspects. And as it turned out, this effect, the Lewis number is the one that determines the Mach-Stinn length, the coefficient. And there is another factor about the curvature aspect. The larger the flame gets curved, effects gets larger. So it's always a product between the actual hydrodynamic action multiplied by the coefficient, and that action part is defined the flame stretch, and which essentially is a definition, a normalized flame surface area, material derivative. And as it, well, again, I don't want to spend too much time of this basic theory of combustion. This is essentially boils down to kinematics. So you only need to care about flame surface as long as you can capture isosurface of the flame front moving along the space, and you can always determine this stretch factor. And there are many, many examples that you can determine in an analytical manner what kind of stretch the flame is subjected to. And it eventually comes up with this final relation. The flame speed is modified with respect to its non-stretched reference condition by the certain factor. So again, this is a fluid dynamic effect, and the Mach-Stinn part is the property of the mixture given by the Lewis number. And in a non-dimensional way, we call it Mach-Stinn number, and the stretch, non-dimensional stretch, is called Mark-Karlovitz number. And those are the two important fluid dynamic parameters combined with the mixture property that determines whether the flame will accelerate or destabilize depending on the system. And there's a further asymptotic analysis that actually derive the expression of the Mach-Stinn number in terms of a Lewis number as well as a heat release parameter. So those are the kind of a brief 10-minute review of the combustion theory. So these are some of the major accomplishments done by asymptotic theory when supercomputer was not around. I just wanted to pause for a minute to appreciate one thing here. In many of these asymptotic analysis, many of the assumptions we made through this derivation was ridiculous. Density was constant. Lewis number is close to 1, vary by order epsilon. It's all unrealistic, right? But look what we've got out of that information. A lot of times, you need to be clever about isolating important physical aspects. In order to do that, sometimes it helps to ignore all the others. Well, this is one big advantage of theory and computation for that matter, as opposed to experimental people. Some people can actually design clever experimental system to achieve that, but it's a whole lot harder. Mathematics, numerical model, well, Lewis number unity, I can set that up in the model and see what happens. And this is, all the students doing research must be intellectually trained to come up with this kind of a conceptual thought experiment. And that's kind of a message I'm trying to get. All right, so intrinsic flame instability, Sivashinsky called it self-turbulization. So flame has intrinsic mechanism to wrinkle its front. Well, so when we talk about turbulent flame propagation, we all talk about the wrinkling surface enhancement. So how much does it matter in actual turbulent combustion system? That is still the contentious, controversial subject. Some of the recent theory, the numerical analysis actually explore that, including one by Poludnenko, who was here during the CCRC conference, and the company. He did this 3D DNS study of the turbulent premixed flame propagation. And this is a turbulence injected into the flame. And he found out actually, this is a front part. You can see the eddy structures are much smaller. Behind the flame is much bigger because of thermal expansion. This picture shows the kinetic energy spectrum. And surprisingly, I don't know if you can see it, but this curve is the reactant side. And this yellow curve is going into the product side. and this is a wave number space. So interestingly, the kinetic energy goes up as you move from reactants to product side in the small scale wave. So there's some kind of a backscatter. This is what we commonly call backscatter, energy cascade. Common sense knowledge is that all the turbulent energy transport comes from large scale to small scale. Energy goes that way, but this is actually going backwards. This is their report. We don't have clear explanation about why such thing is happening, and some people still don't believe it. I've seen some heated debate at conferences, but these are some of these fundamental fluid dynamic aspects of the subject we want to investigate. In terms of combustion modeling aspects, this Lewis number effect is a preferential diffusion, and the general understanding is that that effect will vanish because the Lewis number determines the laminar transport, but as the turbulent mixing dominates in all the flame dynamics, that effect will be overshadowed by turbulent fluctuation. So that's the general qualitative expectation, but there are exceptions. So there was a diffusive thermal instability, which often, I forgot to mention, they occur at two different scales. Diffusive thermal instability, by the inherent nature, is coming from the flame structure. Its scale, physical scale, is always order of flame thickness. Of course, this can be several factors, of course. Hydrodynamic instability, like I showed you, it has nothing to do with flame structure. So its scale is hydrodynamics. What is hydrodynamics? It means it's depend on the system. So the bigger the box, it's the size of the combustion device that limits the growth of this large-scale structure. In my opinion, this is actually a big deal. So I am also raising some contentious points here, but many people working on turbulent combustion in today's community is looking inside this extreme Karlovitz number where the flame structure is shredded, including myself. We are examining that. But ultimately, engineering perspective, we are looking for what's the impact about overall burning rate enhancement. I believe it is the Darius-Landau instability that's creating large-scale bulging, which is system-dependent. I think that is actually the overriding factor. And there are some, again, investigation coming up in recent years, both experimentally and computationally. This is one done by Kreta, my colleague at the University of Rome, and Andy Aspden currently at Newcastle University. They've been examining this type of issues. So this is just an example of Bunsen flame simulation at different device size, the nozzle jet diameter, and you see the shape flame topology changes tremendously. And this is small, well, it's not scaled properly. This is small flame and big flame. Nothing has changed, but because of the sheer hydrodynamic scale, you see a lot of flame area generation. And this is one aspect that often people ignore, and I think this must be taken into account when you're trying to analyze your combustion performance of turbulent combustion systems. Kind of digress, but I will come back to this turbulent subject later on. Right now, in this lecture notes, I'm mostly talking about laminar flames. Markstein number is another, it's kind of, we call it transfer function. So another practical implication of this study is a very strong relevance to acoustic instability of combustion devices. Basically, any acoustic perturbation created inside the chamber due to the resonance of the chamber length or whatsoever will feed back into the flame, and they will change the flame speed. And then there's a well-known Rayleigh criteria, so whether they're in phase, out of phase, you can go crazy and shut down the system. Another aspect we need to keep in mind is that so that this flame response to any imposed oscillation in flow field, which is hand in hand with pressure fluctuation, needs to be investigated. And it's like a black box. In the control theory, you have input oscillation. What's the outcome? Are they amplified, and are they there's a phase lag. Those are two important factors that we care about, which is what we call Markstein transfer function. One message I want to give out of this slide is that we all talked about flame speed response in the kind of this context, where there is a flame speed either decrease or increase proportional to the Karlovitz number with the proportionality constant of Markstein number. Well, this is a kind of quasi-steady context. If you have flame, but a lot of the flow field is unsteady, and this flow field itself has its own time scale. If that time scale oscillates very rapidly, often exceeds the frequency of the flame to respond, then flame acts like a low-pass filter. So it doesn't, beyond certain frequency, it doesn't see that anymore. So this is one example of this Markstein transfer function done in a nice 1D counterflow situation. I just oscillate the inflow velocity, and you can indeed see that flame response just decays down, and there's so-called a cutoff frequency. And that may have an important implication in the designing these gas turbine combustor. So I hope I'm giving you some convincing argument about how this fundamental theory actually serves the design of the practical systems. Because in a nutshell, however complex a device is, locally we have to examine the flow-flame interaction. And this was, by the way, in the context of having a well-structured laminar flame front, which may not be valid, and which is why we want to, in the next lecture, we are going to talk about turbulent combustion regimes, whether the combustion happens in those more flame-like manner, or it can be completely distributed, and that has to be analyzed separately. So this was a kind of a general, the theoretical aspect. So now, modern times, in today, students are looking at laminar flames not by asymptotics, but usually by using Chemkin type of application suite. So let me just give you a brief overview, review of, this is no profound science, but it's just a review of material, just to appreciate what is happening inside the black box without you knowing it. When you push the button of a cloud flame, this is what's going on. So we have governing equation needs to be solved. The mass, momentum, species, and energy, which can be written in convective or conservative form, which is a kind of numerical terms where one expression is better than the others in terms of when after you finite discretize it, the subatomic properties are conserved better. Well, so we have total of n number of species plus 1, 2, 3, 4, 5. So n plus 5 equations to solve. And each of these, the species equation has is a reaction source term, which is becoming a pain. It's thanks to some kinetic model developers like Professor Mani Sarati. He gives me the reaction mechanism with 300 species and 3,000 reaction steps, and that goes directly into the burden. So this is what it takes. So if you want to do it without doing this Linian's asymptotic theory, you have to carve them all into your model. So stress tensor is a standard fluid dynamics, and the heat flux vector, we need to account for all that. This is relatively easy. Although, and then these are all what we call the constitutive relation that constructs all the right-hand side. So if you think about it, well, after all the right-hand side spatial derivatives are all discretized, what we call is a method of lines, meaning this is just a coupled system of ordinary differential equations starting from initial condition, march over time, through whatever time integration schemes. And that's, after all, what's all it is about. So these are constitutive relations. One of the major parts about this detailed chemistry calculation is a chemical reaction source term. Again, so many of you must be familiar with the Chemkin input file, right there, like that. So we have to declare how many species we put in and how many reaction steps we put in. And each of them is curve fitted by Arrhenius kinetic rate constants. And those are all computed in your code. And that goes back into the reaction source term. Every time you march over time by one step, this term must be computed by that formula. It costs a lot of time, but that's what is easily done these days. Computer is so fast, and you can do it rather easily. From computational aspect, one thing to keep in mind is for the given species, well, so this Wi is a reaction source term appearing at every species equation. And this is a summation over K. So roughly, the actual operation count increases with number of reaction steps. So oftentimes people kind of ignore that aspect, but actually computational cost is directly related to the size of the reaction mechanism in addition to number of species. So that's one thing to keep in mind. So if exponential function evaluation goes almost linearly proportional to the number of reaction steps. So to make the computation amenable, we want to reduce both number of species and number of reaction steps. Diffusion velocity, diffusion transport is another important thing, as you may see here. Unless you use a simplified fixed law of diffusion, the species equation has this called the diffusion velocity, which is defined by the lump of the specific species moving velocity with respect to the mean velocity. So there's a bulk mixture moves at one velocity, but different species move differently relative to the bulk velocity. This is exactly the differential diffusion Lewis number effect. And that has to be accounted for following the well-known Stefan-Maxwell relation, which is unfortunately implicit. Again, I don't want to dwell on too much of the math, but just to point out, in order to determine this VI, the equation that we need to solve, even if we ignore all the other secondary terms, it is an implicit expression. So it costs a lot of money and time. And in addition, I need to know elementary species diffusion coefficient, shown right here, and the viscosity and all that needs to be determined. And that is done through this transport kinetic theory. And if you run Chemkin, there is a tran.data that includes all the information about Lennard-Jones parameter and so on, those are molecular parameter. That is done, but actually in the actual computation, once at the beginning of the calculation, these are temperature curve fit. So this is not well known to many users, but again, you don't really have to know it, but that's what is done in the background. Back to the point, the diffusion velocity calculation is not cheap, especially when you want to do it rigorously. And one most rigorous way of doing it is to determine all these binary diffusion coefficient and invert the matrix. And that is often called the L matrix, and this is a rigorous way of doing it. Again, I don't want to get into too much detail, but this is a method followed by Ern and Giovangeli, and there is a software available to download, which is called EG-Lib. And it's very expensive. As you can easily see, well, without taking too much details, this involves matrix inversion. And matrix inversion gets expensive, and the size of the matrix is n, number of species. And as the number of species increases, this computational cost goes like n to square. So remember what I said? Well, there is a k dependence for chemical reaction source term. Of course, there's an n to it because your number of equations increase. So basically, that's another computational cost, but transport alone, it adds to amazing amount of computational cost if you are dealing with hundreds of species. So, which is why today's great majority of the modern DNS LES code that deals with detailed species are not using this type of multi-component formula, this is named as multi-component property formula, but instead much simpler mixture average formula, which is a kind of weighted average of individual species transport terms, including the diffusion velocity is done by this explicit expression instead of inverting the matrices. So this is at least proportional to n, not n squared. So it is cost is much cheaper. So this is by far the dominant, commonly adopted practice in today. So that's what goes behind it. Is a kind of mundane, kind of a routine discussion about what's inside the black box. And just the last maybe 10 minutes of discussion, I'm going to just go over with what kind of laminar flames are usually modeled inside in your computer. And that is, again, I call it canonical laminar flames. And this is relatively easier to set in your laboratory. And before you go into detailed combustion problems, turbulent combustion system, you want to validate your mechanism, and you want to validate your flame speed, you want to validate the extinction strain rate, and those are all done in this type of canonical laminar flames. So I'll give you a few examples. First is a homogeneous reactor. That's as easy as it gets. What you need to solve for is a 0D temporal time integration. So I just have a box full of homogeneous mixture at a given fuel air composition, and at the initial setting of the temperature, pressure condition, and I'll let it go, and this will time integrate over, and then you will see something like that. So temperature, it'll ignite and it'll go up. Again, this is not steady diagram. This will show you exact temporal evolution dynamics. Once again, as I said, if you want to make this happen, you have to be outside the turning point, ignition turning point of the S-curve in terms of Damkohler number. So if you set up temperature of the system to be 300 K with the stoichiometric mixture, 1 atm, it'll never go. It'll keep going forever. You can ignite it in different ways. You can do it in the constant pressure system or constant volume system. Equation can be easily modified by either using CP versus CV. Or some Chemkin type of application code, call it fancy way. It's an engine module, IC engine module. But what it really is a still same homogeneous box without valves, except the volume change over time through the crank angle degree is prescribed by this volume as a function of time. So there's a crank angle data as a put into the system, and you can get a formula easily from the kinematics of the crank angle and connecting rod. You can find out the VT as a function of time. And those can be done and integrated, and you can get the answer. So this is a kind of the simplest and the most commonly practiced computational model in the whole Chemkin suite. I would like to just briefly mention the associated numerical methods that you need to worry about. In this case, everything you need to worry about is a time integration scheme. And I'll get to that a little bit more in a moment. But time step is determined by how rapidly your system changes. If you miss that, either system numerics goes unstable, or you can get a wrong answer. So those are a lot of times is a chemical time scale. We are dealing with, remember, the hundreds of species and thousands of reaction steps. And a lot of those are done routinely today. So detailed mechanism can be run on Chemkin box in a matter of a few seconds or few minutes. And then the Chemkin is built with is a sophisticated time integration scheme. And so it can be done by explicit time integration or backward differentiation. This is one of the most forgiving and accurate variable coefficient multi-step time integration scheme. It's called the CVOD, and that is utilized in Chemkin suite. I'm going to get back to this time integration issue later on, but just stay tuned. The next sophisticated model is still homogeneous, but so-called the stirred tank reactor, which is basically, in a simplest manner, you have a box and you have a flow in and out, and what comes out is not equilibrium, but instead you have only finite amount of residence time. And that is manifested in this tau of the CSTR. So we call it continuous stirred tank reactor, CSTR. And this is a characteristic time which is defined by the overall, the volume divided by the volume flow rate, then you determine the residence time. So if you pass it through too quickly, then the mixture will leave unburned. So it is the same unsteady calculation, but there's an extra time scale, characteristic time inside the reactor will adjust the burning rate. So that is this model can be further sophisticated by allowing for different zones inside the reactor. This is typical chemical engineering approach to allow relatively homogeneous system, but there are slight variation in the composition. Then you can subdivide into zones, and each zone is interacting with each other by certain approximation, which is F function shown right here. It's a kind of interaction between two representative zones. And it's kind of analogous to transport, except it's a more heuristically model. I'm discussing this because actually this is surprisingly commonly adopted submodels for large-scale turbulent combustion simulation. This is a different variation of this type of concept. It's called multi-zone model, or even like a PASR, partially stirred reactor. So I'll get to that part in the second part of the lecture. Now, this is a famous premixed flame code. Again, Professor Maruta discussed it yesterday extensively. This is a steady equation. You have a one-dimensional, either freely propagating inside double infinite domain, and this one sets up as a reference premixed flame speed. And everyone wants to know that if you pick stoichiometric methane air mixture, I want to know the flame speed. That speed is unique property of the mixture given thermodynamic condition. And it is the most fundamental quantity that we need to have in mind. And everything else varies as a function of strain rate and heat loss, and then those variations can happen. So this is such a convenient tool to do it, and this is how, indeed, many mechanism developers are fine-tuning their mechanism rate constants by trying to match the same flame speed that's measured inside the experimental laboratory. Just wanted to also add the comment that the standard premix code is offered in two different versions. One is a freely propagating, like I just said, or alternatively, you can convert it into the burner stabilized flame version, where you can have an input boundary condition at the burner exit, defining the temperature and everything. In that case, the mass flux, the main difference mathematically between the two is that in the freely propagating flame, this m dot, this is a flux rate, because you are sitting on the flame front and flow is coming at you instead of flame going into the channel. And that burning velocity in a steady solution, it has to be only one and only value. So this is what we call the burning rate eigenvalue. So solution procedure is essentially iterative procedure. It's after you discretize everything, it is a system of algebraic equations, nonlinear algebraic equation. You need to iterate by guessing and correcting until you get the final solution for the bullseye value for m dot, and that's your burning rate constant. That's done through a typical Newton-Raphson iteration technique, which is for the Chemkin-specific code is called the two-point. And then it involves adaptive grid refinement because you need to resolve the flame structure. Although today's computer speed, if you don't want to hassle with that, you can just grid it up. 3,000 grid points across 1 centimeter length. It's easy. You can still do it on the desktop. Okay, so that's the premix code. And finally, the counterflow. This is, again, the most commonly used. And not too many people today, in today's combustion world, know about it because everybody's using Optiv. But before that, actually, the Mitch Smook designed this more like a theoretical formulation about doubly infinite counterflow, which is consistent with Linian's mathematical model. So here, actually, fuel and oxidizer come from infinitely far away, and that way you can construct nice theoretical Hemans flow field. for which velocity field is well described by this formula, where A is a constant, it's a strain rate parameter. So one advantage of that is you can prescribe exact strain rate before you start computation. The downside of it is you can't construct it in the lab. So this was earlier, from computational standpoint, this was easier to derive, and this has been first used by Smoke when he was together with the Bob Key in Sandia lab, and they did this kind of analysis and reported the result. And people started to build a burner, and well, I can't do that. I have finite dimension of the burner. So that's why Optiv came out. It was actually, the SAN report came out in 1990s by Andy Lutz. And well, many people misspell name Optiv, so keep in mind this is official name of the code. Well, it's all part of the Chemkin today, so it doesn't really matter much. So main thing here is that this was a reconfiguration of the computation, the mathematical formulation, once again axisymmetric, but in the finite domain. So here, just like experiment, you can prescribe the velocity at both nozzle any way you want, and you can determine the flow field. And the effective strain rate, the one downside is that you have to compute it afterwards. So there's a trade-off. One way is allows very nice systematic parametric sweep by changing A from certain range of the conditions, but the other one is easier to compare against the experiment directly. So that's the more commonly used today because everybody running this simulation compares with the actual burner experiment. What I contributed at Sandia during my postdoc time was to extend this Optiv code into Unsteady simulation, and still this is not part of official Chemkin suite. I just wanted to have Unsteady version so that I can impose some oscillation, and I gave you some example of what kind of studies can be done by doing that. It turned out to be quite a non-trivial task, and again, aside, I don't want to spend too much time on it, but as it turned out, I had to do some compressible treatment of the equation, and that to ensure. Originally, the equation was written in incompressible low Mach number format, but I had to reintroduce back some level of compressibility effect, to stabilize the computation. So here, once you do that, still the whole equation system becomes a differential algebraic equation system, and that requires the DAE solver. And more on that discussion later. So this was kind of a mathematical computational trick to play. And this code is available with me, and whoever wants to investigate in the burner by imposing the acoustic impulse to investigate flame studies, I can provide the code. It's not official, but I have the source code to share with you. So like I said, this Optiv, you need to compute the strain rate. Strain rate is what determines the Damkohler number. So like I said, Counterflow is a very nice device to independently control flow resistance time by changing the strain rate. The Smoke way is shown here. This is a typical axial velocity profile between the two nozzles. If you follow Smoke's formulation, it'll be doubly the linear profile toward the end, so which is unrealistic. But still, the advantage is that you impose A and the rest is determined, and that's the potential flow formulation. The opposed jet, you impose the velocity here, and then you compute everything, and by the velocity gradient, you can extract out the actual strain rate value. It can be done more rigorously by the velocity gradient, or you can follow some kind of empirical formula, because if you do it rigorously, then you are asking the experimental people to do the LDV measurement of the velocity across the center line. And not all groups have that capability, so often experimental group reports the global quantity of the strain rate, which is often using the Shadry-Williams formula. The real burner system is probably Optiv can be done again following that track, because what the difference between the two means is at the nozzle exit, the velocity is not perfectly plug flow. You may have some divergence of the velocity coming out. So you can, but Chemkin actually Optiv allows to have the tangential velocity value as a finite. Although if you want to match with the experiment, you need to know exactly what those are. So in all practical purposes, people end up not using it, but there's a way of accommodating it. The real flow is expected to be somewhere in between plug flow and smoke in between, and that's what you're going to measure out of your burner experiment. Well, those are minor details, but the ultimate message is these are overall slope here, it determines the flow resistance time, which now we commonly call strain rate, and that is directly related to the Damkohler number. So increasing the strain rate will reduce Damkohler number. So that's a nice way of reproducing S-curve turning point. You can start from frozen solution to ignite. You can do the extinction experiment, and those are all done in this counterflow burner. And often now we will move into next hour, we will be talking about the turbulent combustion modeling and how that strain rate in the counterflow configuration relates to turbulent flame modeling context is through the scalar dissipation rate. Okay, scalar dissipation rate is defined as this formula, which is a function of the gradient of mixture fraction variable z. The mixture fraction is a conserved scalar, meaning this is a one nice property, some linear combination of, you can think of it as without further complication of the derivation, you can think of it as an elemental mass fraction. Throughout the combustion, the fuel disappears, and then product shows up. But throughout the whole process, if you realize the total number of carbon doesn't change. And so, and neither does hydrogen, H atom. So all these, if you keep track of this elemental mass fraction, they are inert to chemical reaction. How great is that? So if you derive the transport equation for this elemental mass fraction, the transport equation for that elemental mass fraction has no reaction source term. So you are doing combustion problems, but you are solving for non-reactive problems. That's a great computational savings. So that's the idea behind this mixture fraction. And in fact, real mixture fraction is defined in this typically the Bilger's way, in order to allow for understanding that different species move differently due to the different diffusion. So this is a kind of, it's not rigorous derivation, it's an empirical compromise to account for that between C, H, and O elemental mass fraction. If you compute elemental mass fraction out of your flame calculation, you will find out that they are all slightly different. So this is a kind of weighted average just to accommodate those differential diffusion effect. But like I said, in general, large turbulent combustion, this effect is expected to vanish. So a lot of time, there have been sophisticated refinement of the Flamelet theory to account for this Lewis number effect, but those are usually not commonly adapted in actual simulations. So, well, one advantage of this elemental mass fraction is this one serves as an actual coordinate instead of physical coordinate. Just to give you an example, so here is a jet flame coming out from the fuel and oxidizer. So this is a flame front. So if I take a cross cut anywhere, you will find the one-dimensional diffusion flame structure. But if you plot them on the physical coordinate, they will all different. They will have different thickness and all that. You cannot easily overlap. However, if you determine the mixture fraction, which is defined as 0 in the oxidizer, 1 in the fuel side, on that coordinate system, everything falls back together because Z scales back to 0 to 1. And that looks just like that. So every crosscut you have will fall back on this single curve. Whether this will be close to that versus that depends on the local strain rate, which is called the scalar dissipation rate right here. So this is a kind of prelude to general framework of the Flamelet approach. As long as your turbulent combustion burns like that, you can simplify the chemical reaction by solving for the so-called Flamelet equation only. And transport of this part in the 3D code can only deal with the non-reactive transport equation for mixture fraction. So this is one of the most commonly used higher advanced turbulent combustion submodels, which is more rigorous compared to other empirical submodels like multi-zone or PASR. One last point that I would like to note is we need to, well, how do I generate this turning point? Well, I said all this S-curve behavior. You can do that, and actually current commercial version of Optif allows this turning away, but it's not easy. As you can see in this example, it stopped right there. So it's not as trivial to turn it over to reproduce actual turning point behavior. And there are two methods to do that. One is called the arc length continuation. The other one is a flame controlling continuation. Again, well, I think in the interest of time, I'm not going to dwell on this detailed discussion here, but there are methods available to allow to do that. So this is, I think I'm going to speed up a little bit. So this is NTC behavior showing. So this was in response to the earlier question about how does this S-curve manifest in complex reactive system. So here is one example. So everybody knows pretty much about this NTC chemistry. So when you are dealing with complex fuel, typical fuel like engine fuel, N-heptane, ignition delay time over temperature curve, you find this kind of behavior. It's not single exponential curve, but there is a certain bend in the curve. Well, it can go to negative slope, which is literally called NTC, but it doesn't have to be, but there's some kink. And we all know why it is happening. But what it goes to tell you is basically the dominant chemistry changes as you move from here to this region, and that difference is manifested by different types of turning point. So each different dominant reaction, ignition chemistry is nonlinear. They will create this the ignition turning point. So which is shown here. Don't pay attention to these different colors of the curve. But this is the equivalent S-curve, but it looks a lot more complicated. Strain rate is the inverse of the Damkohler number. So strain rate is decreased. This is actually going to the positive axis of Damkohler number. So notice what happens. If we start from here. As the strain rate decreases, you have a turning. So this is the ignition. But this ignition doesn't jump up to the fully burning flame condition. Instead, it reaches here. And this is called the cool flame, dominated by different types of chemistry. Now you reduce the strain rate further, increase the Damkohler number, then you go along this line, and then you jump up again, and then you have hot burning, so which is shown in this figure. So this is a very intricate experiment. You can actually realize inside the lab to have this cool diffusion flame and hot diffusion flame. And this dynamics, is sophisticated dynamics can be captured by these multiple branches of the turning point. So in summary, this S-curve dynamics is real, and you do have all this, however complicated, you can reproduce that in any complex chemical system. Whether this minor blip is important or not depends on your context of the problem. And indeed, you can reproduce this turning point at different pressure condition and find out whether this cool flame chemistry matters more or not. And so there's practically one-to-one correspondence in between. Finally, I'll just skip through it. You can use this Opus code to analyze unsteady ignition phenomena. So again, this is something that cannot be easily done in the lab. You can't imagine measuring ignition delay time in counterflow. You either have frozen or fully burning. You'll approach over the turning point, it'll jump up. But once you put your system into the beyond the turning point regime, you can actually do these steady ignition phenomena. So this is some of the work that I did some years ago about counterflow ignition. As a steady condition, you can reproduce this two-stage ignition problem. This is an unsteady time integration in the counterflow. And you can twist it around by oscillating. While things are evolving, you can oscillate strain rate to see all these different types of ignition pattern. But those are the rest of the detail. I'm just trying to point out these unsteady dynamics can be captured in a different way and requires different types of mathematical model. Okay, so that concludes the first part of my lecture today. I'll try to make it more dynamic in the second half, but the main key summary is that combustion dynamics is highly nonlinear, and the main reason for this nonlinearity is coming from exponential nonlinearity. And the Damkohler number serves as an important system parameter that determines the flame combustion state. I hope you appreciated the distinction between the steady versus unsteady description. And another message I would like to convey is a theoretical model doesn't have to be physically correct to be good. You can get a lot of insight by making some outrageous assumptions just to rule out all other effects that you don't want to consider, and you can isolate important aspects. Now, today, the simple flames, the first principle calculation can be easily done on a desktop, so that makes our life very easy to estimate and validate all these models. However, again, one must always go back to the fundamentals and try to see where they're going. And these canonical flames are widely understood. And after the break, I will try to extend this whole concept and the tools and the methods into understanding realistic turbulent combustion system, mainly based on the modeling exercise. Okay, so with that, thank you, and I'll be happy to take any more questions before we go for a break. Yes?
Well, you already had a question.
Professor, thanks for answering that. That was really very educating. Just a quick one. In real systems, to my understanding, most phenomena are stochastic. For example, we talk about ignition. Now, let's assume if there are 100 parcels in a system, some of them may ignite earlier. They may reach the burning mode for ignition faster than the others. So how does the theory that we have at present tries to capture that part of it? Right now, we are assuming maybe all the system is at steady state with uniform conditions and all that.
Well, yeah, that's exactly the first starting point of my next lecture.
Okay.
So, well, you need to, it's a statistics.
Right.
So this stochastic phenomena is done through the statistical prediction, which is done by the standard probability density function. So, but this PDF requires individual deterministic point, and this stochastic part is handled through this statistical analysis. But each of these instantaneous sample points are deterministic, and that is provided by this laminar flame solution. So I hope you will have a little bit better idea when we discuss in the next class about turbulent combustion modeling.
Yeah, thank you for the lecture. You had a slide up there showing just before the optive calculations, the infinite solution, infinitely separable jets. The paper by
Yeah. Okay.
that one.
Yep.
So I just wanted to highlight something to all the students here. Puri, Seshadri, Smook, and Keys. By the way, Keys is David E. Keys, who is now the director of our Extreme Computing Research Center. And you see 30 years ago, he was writing a paper about combustion. So think about who you're sitting next to. and where this person will be in the future. May not necessarily be in the field of combustion, but can have impact in other areas. Now, I come back to the question I had, is you had the few more slides before about premixed flames. I was wondering, it's an eigenvalue problem to get the laminar flame speed. Oftentimes we run these simulations and we don't find the grid-independent solution. Why is the grid independence so important to determining the laminar flame speed appropriately or correctly?
Well, so numerical errors is proportional to the grid size. So we need to get grid-independent solution.
And can you explain why that's needed in terms of what's happening in the calculation which does not allow you to have that grid independence?
Well, so this is the basics of any CFD. You want to make sure, this is not a CFD class, so I don't have time to talk about that, but every differential derivative terms are represented by finite difference, which is basically dy dx is a y I plus 1 minus yi minus 1 divided by 2 delta x. It's a central differencing. So that error is proportional to delta x to a certain power. If it's linearly proportional, it's called the first order method. If it's a square dependent, it's called second order. So the higher order methods are usually better to preserve better accuracy. In any case, you want to refine the grid. Every exercise you have to refine the grid size until you see the solution doesn't change, which is what we call, because the numerical truncation error of the finite difference approximation vanishes into that direction. Usual conventional Chemkin type of application is using adaptive gridding, so which makes it a little bit difficult to do this full grid refinement test. So people it's not actually as easy considering all these reaction nonlinearity, and you will find some of the species profiles are very, very thin, especially if you are dealing with like a biofuel chemistry. So you have to be careful. Like I said though, well, unless we are talking about 10,000 reaction steps, most of these calculations today can be run on a desktop scale computing, even if you have 3,000 grid points. So usual domain size, again, domain size needs to be determined. So again, these are numerical basics. So yeah. Does it address your question? I guess you are raising it for kind of tutorial purpose. Please.
Yeah. Thank you, sir, for an excellent presentation. I have just one simple question about the mixture fraction. If one have a system where there is flue gas recirculation with some carbon dioxide in it, how does one track the mixture fraction in the reaction zone or in the combustion region when there maybe the CO2 that recirculates maybe participates in the reaction?
That's actually a good question. So general mixture fraction definition in your system requires, in a basic way, there are people who refine that, requires two distinct definable streams of fuel and air, oxidizer. So here fuel can be diluted at given temperature. There in the air side is represented by a single stream of certain oxygen, nitrogen. Now if you want to throw in extra EGR gas recycled from external source, this really messes up the whole thing. So if you really want to analyze those particular scenario of reintroducing EGR, you have to consider this three-stream mixture. So it is a little bit modeling challenge. People have come up with some idea of how to handle that, including those Stanford group, Matthias Ime, and there are a few other groups who have worked on these multiple, more than two streams, and this mixture fraction formulation has been extended. The same similar thing happens now while we're at it. When you have a liquid fuel, same thing happens. As you initially start with the fuel-air mixture, but the fuel concentration per se at the fuel stream keeps changing as the liquid droplet is evaporating. So fuel stream is usually, we define it based on gas phase. The fuel mass fraction keeps changing. So in that sense, one boundary stream of the mixture fraction space is not fixed. So there are ways to handle those issues. And if you have any specific issues in your research, we can discuss that later offline.
So I have a question. So you talked in the beginning of the presentation about the theories of stabilization of a gaseous fuel. Have you done any mechanisms, or stabilization mechanisms or theory of a spray flame?
Spray stabilization?
Yeah.
Well, we need to be a little bit clear about the terminology here. Stability and stabilizations, those are kind of similar words, but they have quite different meanings. For example, if you are referring to flame stabilization behind bluff body, for example, those are not this kind of intrinsic flame stability. And in fact, even in terms of flame stabilization, the mechanism can be completely different. You can think about blowout, which is the case when the hydrodynamics is pushing the flame out, regardless of flame intensity. It is not extinction. But blow off is when the flame gets weak by the anchoring point, so flame extinguishes, cannot hold up, and goes away. It looks the same way as a flame disappearance, but the fundamental mechanism from the fundamental standpoint is completely different. So those, well, so back to the spray, I don't know what exactly we're looking at, but spray is same thing. So just my message is that you have to be a little bit careful whenever you're talking about disappearance flame. It doesn't necessarily mean flame is extinguished. Depending on the context, it can be simply, especially in the case of premixed flame, it can be just flame just blown out, which is different from blow off.
Okay. Thank you.
Yeah, thank you. Everybody ready for coffee? There's one more.
Thank you for your presentation. So going back to the dispersion relations, would you mind explaining the physical meaning of this and what specifically would be the wave number of a flame?
So dispersion relation is ultimately the final analytical relation between omega and K. So let's take a look at the method of normal modes. So these are the F is a flame front. So F equals 0 is a flat front. So let me give you an example. So I have a flat flame. There's no disturbance in the flame, the flow field. So I'll slowly curve it by sine wave. So K, in that case, is my input parameter. I can wrinkle it any way I want within given wave number, wavelength. And then I have a slight perturbation. And that I'm watching how that perturbation amplitude grows over time, which is described by this function omega t. So omega is called the growth rate. And in general, this is all complex number, but what we care is the real value of omega. When that real value is positive, you can see that exponential function will blow up. When omega of real value is negative, it'll dissipate, decay down. So it is stability. So what we care is the real value of omega out of this dispersion relation as a function of K. In this case, this is a note that this is a quadratic equation. So I have two solutions, two roots. And you have to be always conservative in stability analysis. You have to be stable for all cases. So both of the solutions must satisfy the stability condition. And one of the solutions here is shown that real value of omega is positive. So it is a proof that things will go unstable. So that's how we tell. It is an onset analysis. Linear stability analysis tells you about initial thing. It does not mean amplitude will go infinity, because then the whole linearization assumption breaks down. So you'll have to do extra nonlinear analysis. But at that point, in today's world, we do numerical simulation. So indeed, what you do DNS of this flame, you will find out that flame will be wrinkled, and it'll be saturated at certain amplitude. which is the effect of the nonlinear aspects. Does that answer your question?
Yes, thank you.
Understand the meaning of omega and k. This is an input, this is a response. If this is a positive, unstable, negative, stable. More questions over way back. But that is not this restricted region. You are not allowed to sit there. We should forfeit their right to ask questions.
This is a fundamental question I was curious to ask you. In the numerical simulations, how are you initiating the combustion?
How do we initiate?
Yeah.
So you have to ignite it, right? So it depends on whether you care about those initial transient. If you do, then you have to make your initial condition realistic. A lot of times it's difficult to do because spark is really difficult to mimic, for example. So oftentimes we usually create some artificial spark without too much paying attention to exact details of how they evolve. Once flame is triggered, you'll watch how the flame propagates.
Yeah, so that in the domain, in the numerical domain, how do you decide you told you will create some artificial spot where generally, I think you'll assign some high temperature there?
Yeah, again, depends on whether you care.
So,
if you don't care how it ignites.
How do you design the kind of
temperature peak is usual, Gaussian temperature peak.
Okay.
If the peak is high enough. So, this goes back to the typical minimum ignition energy kind of argument. There's an empirical expression. So you can try out until, so if you do the full unsteady simulation with the temperature spike, if the amount of energy you put in was right, you can eventually have it run into the flame solution. Otherwise, you'll have to restart and intensify the ignition source.
And my second question is, how do you give the input to turbulence in the simulation?
Turbulence input, okay. That's all right. Those are all kind of, that's a practice, you have to generate the turbulent flow. You can do it two different ways. In the engineering simulation, I'm going to show you later about some typical jet flame simulation. You have a pipe. So just imagine what happens inside the actual engine, inside the laboratory. If you have a jet flame with all these turbulent flame anchored, there is a turbulence coming into the pipe. So yes, it is a big question about how to represent that by the modeling. Of course, the ideal way of doing it is you run cold pipe with turbulent flow simulation with the proper length, and you will develop turbulence. Even that is usually sometimes not easy unless you create some initial disturbance. The transition to turbulence in a laminar pipe is going to be probably longer. So those are one ideal way of doing it. Oftentimes it's too much overkill, then people end up doing initial random turbulence energy spectrum, do the Fourier transform into the velocity field in the real space, and they just feed it into at the inlet.
Yeah, I was just curious to know what is the recent kind of developments in it.
Yeah, this is indeed the ongoing research subject. You have to be careful about whether your solution is sensitive to your inflow condition.
The last question is, what CFL numbers are you using in your numerical simulation?
CFL numbers are, reacting, okay, so we are going into more detailed discussion about CFD, which will be subject of the next lecture. But let me go back to, so if you are doing explicit time integration of the equation, you have to, if everything's explicit, where was the, right? So this is a method of lines, basically. So these are all the things on the right-hand side is a forcing function, and that's one way to look at it, and you are integrating over time. And that delta t is dictated by the time scale of individual processes. And so you have to impose, if you impose that process based on convection, that's called CFL. So you need to pick the convective velocity of your system and pick the worst case scenario and make sure delta T is smaller than that. There is another criterion based on diffusion term, and there's another one based on reaction. And so we call it, sometimes people call it reaction CFL, which is a misnomer. Well, the bottom line is actually oftentimes in this kind of integration, reaction source term is the most demanding one. And I'll spend some time on that. I have some points to make, so that will be following up in the second lecture. Okay?
Thanks a lot. Thanks a lot.
This second part is actually a little longer, but actually toward the end I gave a lot of examples, but I understand there is a demo tomorrow, Manny? Right? So there will be some demonstration. So if I'm running out of time, I'll probably skip that part, and you'll have a chance to see that. So let's see how it goes. So welcome back. Let's resume. So with all these fundamental knowledge, we are ready to jump onto complex turbulent combustion problems. So this lecture notes is about we'll start with the combustion regimes, and then the rest of the discussion will be broken into 3 parts: DNS, LES, RANS. I am not going to focus too much on scientific issues that are dealt with, which you can find from scientific studies. My focus will be rather on associated computational issues and how we can achieve accurate high-fidelity simulations of DNS, LES, RANS in its own right, summary of mainstream combustion submodels, and those are going to be main subject to discuss. And then, time permitting, I will give you some examples of the ongoing effort in my laboratory, but again, it seems like I'm going to run out of time. So regimes. Well, everybody in this audience must have seen at least once or twice these famous regime diagrams. And why we care about that is because turbulence-flame interaction happens in different ways, depending on the regimes. So, yeah, why do we care about combustion regimes? Again, what is the main challenge of a combustion in turbulent context is demonstrated in this, well, let me open the pointer. Laser pointer in. So this is a reaction source term in the simplest form. There is an exponential term. It's always this exponential nonlinearity that is killing the problems. It's most challenging. So imagine you have, this is a species concentration. That's the temperature. So now we have a turbulent system. Locally, there's a fluctuation of species and temperature. Assuming that this prime quantity is small, even compared to the mean, still when you feed it in, and what we want to do is we don't want to resolve every detail. We want to have an average quantity, which is called the bar. So let's plug it in and take the bar operation. And by definition, bar on top of prime vanishes in a linear manner. However, the exponential term cannot be simply ignored. If you do the Taylor expansion and summarize, what you find is that the reaction rate as a mean is different from the reaction rate computed based on the mean quantity of temperature and species, but there is extra term, which is a function of T prime. And depending on this E, which is activation energy, I told you it is large usually. So actually this term may be as big or even bigger than the mean value. So if you don't do anything about RANS calculation, each cell you have representative temperature concentration, but there is a small fluctuations. Suppose if you ignore them all, then you are completely mispredicting the actual reaction rate inside a cell. So this is a whole challenge about combustion closure in the entire combustion model. So you have to do that. As a kind of, I will repeat this argument later on. The first point is a turbulent fluctuation create feedback into nonlinear reaction. That becomes a real challenge. And you cannot resolve everything in engineering simulation. You have to kind of have a filtered or averaged information. When you do that, typically I'm talking about the example of large eddy simulation, where small scale, we call it filtered, subgrid level information is approximated based on the knowledge of large scale. I will elaborate on that more later, but the whole notion is built around the concept that it can be extrapolated because we know the turbulence spectrum. Essentially, in other words, in the general turbulence modeling, turbulent flow field, the kinetic energy, all that the small scale does is usually the energy drain. That's the picture of the Kolmogorov scale. So, which is fine. So I can ignore that, and I can easily approximate it based on good knowledge of the large scale motion. Unfortunately, combustion is totally different. Where does a combustion happen? It happens at the small scale. Combustion is about molecular reaction. So combustion, most important chemical reaction happens at the smallest scale of your computation, which you don't resolve. You cannot resolve it in any engineering simulation. So how am I supposed to model that? I can't do any extrapolation because there's no information at the large scale. So that's the main really the challenge about turbulent combustion modeling. The reaction term closure cannot be done in a similar way of the kinetic scalar energy transport. So it has to be done in a entirely from different perspectives. And which is why you have to be a little bit clever, because the way this subgrid chemical reaction happens can be completely different depending on the combustion context, whether it's non-premixed or premixed, or depending on relative interaction between turbulence and combustion. You have to tackle that in a different way. And oftentimes that is a little bit smarter way of doing it. And therefore, that's why we want to characterize turbulent combustion, interaction between turbulence and reaction first, so we can strategize depending on what regime you're at. You can come up with the most optimal modeling closure in each cases. And oftentimes I will revisit that later. This, as such, because the reaction source term, this W bar, has to be modeled entirely, oftentimes the notion is still similar, even if there's a fundamental difference between RANS and LES. Again, that point I will elaborate. But combustion modeling concept is still shared in common with some minor adjustments to ensure the consistency. So that's the whole picture here, and that's the main discussion we're going to have. So I will first talk about how we characterize the combustion regimes, and we will talk about what we do. Without these, you do DNS. Great, you can resolve everything, but you can't do so much. So we'll end up doing LES and RANS, and then we'll have to worry about subgrid and Reynolds modeling. So here's 101 of turbulence. So the general Kolmogorov theory, we are just simplifying everything is homogeneous and isotropic, so we don't worry about boundary layer and all those specific details. So general idea is the energy cascade concept, right? So does everyone know about that? Have you studied this? Students especially? Have you taken, well, so this is a basic subject about statistical description. I'll give you 1 minute summary of that. So basically what is believed is that turbulence is characterized by a whole bunch of eddies. Eddies are just circular motion, fluid motion. And there are scales of eddies depending on the diameter and spinning velocity. You can characterize a turbulence in terms of velocity scale, which is called U prime, and L is a length scale. Diameter, circumference, it doesn't really matter. That's only a factor of 3. So in terms of all scaling purpose, it's kind of on the ballpark. So we have large eddies, which we call integral eddies, and this energy cascade down into smaller and smaller eddies. That's the general concept. In the three-dimensional world, energy is passed down into the, in a steady spectrum, then this energy dissipation rate must be constant at all scales until it goes to the minimum size. So the first assumption of Kolmogorov is this constant energy flux. And what is that? Based on this U prime and L, it is a dimensional analysis tells you it's energy over time, and quickly you can conclude that it's going to be U prime cube over L. So this is what we call the universality scale invariance, meaning that if you sit here or there, if you zoom in and zoom out and overlap together, they look all the same, as long as you are in the middle of this inertial range. That's the basic concept about. And then where does it end? That's the next question. It ends as the eddy size shrinks down into smaller and smaller, and the molecular dissipation, diffusion start to play a role. So that scale can be estimated based on the molecular diffusion and energy dissipation. So it's all dimensional analysis, chapter 7 of fluid mechanics book, pi theorem, and you can easily get that. All right, so that's so these are the summary of the length and time scale to characterize turbulence at two extreme scales. Integral scale eddies, which is typically the large scale motion, which is proportional to the device size. Velocity scale is a kinetic energy. It's a fluctuating component only. And if you know length and velocity, you can get time. And the Reynolds number is a non-dimensional parameter that you use to indicate the intensity of your turbulence. Kolmogorov length can be estimated based on dissipation. It's a molecular event. And the corresponding velocity scale can also be estimated by the dimensional analysis. And then once you know velocity and length, you get time. So this is all Kolmogorov scale characteristics. And by definition, what is the Reynolds number at Kolmogorov scale? By definition, this is where molecular diffusion happens. The Reynolds number is 1. One important, the outcome of that is important thing to remember is the length scale ratio, time scale ratio between integral scale and Kolmogorov scale scales with Reynolds number to the square root. And this, which means the larger the Reynolds number, the scale disparity gets bigger and bigger, both in terms of length scale as well as time scale. And this is indeed the most challenging issue about simulation of large Reynolds number turbulence, because you need to capture the device at the same time you need to resolve all the smallest eddies. So that's, you can't do that. And the dynamic range gets larger and larger as the Reynolds number increases. So those are basics of turbulence. Now, when we introduce flames, you have to worry about these combustion aspects. Then flame is, has a length and speed. Flame speed we already discussed earlier. And length is governed by the molecular transport inside the preheat zone. So it is governed by the diffusivity. Here I'm making an assumption that alpha and nu are roughly the same. And flame time. So flame time is nominally defined as a time for a flame to sweep through one flame thickness. That's a flame time. And Damkohler number I define is a ratio between, so we are introducing now turbulence Damkohler number, turbulent Damkohler number. The turbulent Damkohler number is defined by the ratio, same thing, flow time versus flame time. What flow time? There are multiple different flow time all the way from integral to Kolmogorov. So we pick integral time. That is the original integral scale Damkohler number definition. Well, I don't have to do that, of course. I pick the flow time of the Kolmogorov eddy, which spins much faster, it's shorter. That ratio, I'm going to call it Damkohler number based on Kolmogorov. So that's the Damkohler number can be defined differently depending on your flow time scale, which varies over the spectrum of turbulent eddies. So this is Damkohler number integral, Damkohler number Kolmogorov. I think this is a perfectly rational way of defining it. Unfortunately, the rest of the community calls it Karlovitz number, and they defined it upside down. So large Karlovitz number corresponds to small Karlovitz Damkohler number. And I really hate that personally, but I can't go against the mainstream, so I keep complaining. And so that's the Karlovitz number as we know. Karlovitz number is effectively timescale ratio between flame time to Kolmogorov timescale. Why it matters will be evident as I show you later. And then there are useful relations connecting Reynolds, Damkohler, and all together. So this is a beginning of the forming. So what is the main thing here? So Reynolds number, as you know, is a non-dimensional indicator about intensity of turbulence. It's a ratio of turbulent timescale to the molecular viscous timescale, right? So Reynolds number large means the turbulence is more intense. Damkohler number is the ratio of the chemical to the flow intensity. So high Damkohler number means we are closer to the intense reaction. So those are two axes. Reynolds number everybody is familiar with. Damkohler number is the intensity of the reaction. So those two serve as a perfectly nice two reference axes to explore combustion regimes. And unfortunately, people don't do that. So why does it matter? So it is when you characterize turbulence, chemistry, flame interaction, so it's all about time scale. Or time scale is easily converted to length scale. So one of the important thresholds of dictating the flame behavior is so-called the Klimoff-Williams criterion. Well, by the way, you can, without too difficulty, you can easily derive the fact that Karlovitz number, once again, it's TF versus tau K, is a length scale ratio squared. Okay? So it's good to keep in mind. And when that Karlovitz number equals 1, what it means is the flame thickness, which is shown right here, the propagating premixed flame, with respect to the Kolmogorov eddies, which is the smallest eddy you can think of, becomes equal. So what happens as your Reynolds number increases? In a fixed box, imagine you're stirring it with a fan. The fan size will determine integral scale eddies. And as you spin it, turn the fan faster and faster, what happens is the integral scale is fixed, but small scale eddies get smaller and smaller and smaller, right? So there comes a point where this eddy, Kolmogorov eddy, becomes comparable to the flame thickness. That's when these eddies start to penetrate inside the flame and shred it up. So then you can't say flame retains this nice one-dimensional laminar flame structure. So this is well-known Klimoff-Williams criteria. The condition is a Karlovitz number of 1. So just keep in mind the meaning of unity Karlovitz number. So that's the original threshold of determining whether you can treat the turbulent combustion to be more flame-like versus more distributed. Some years later, Peters argued that Norbert Peters, who passed away, brilliant scholar, theoretician, he is coming from Flamelet school. So every Flamelet school people wants to justify that Flamelet assumption is valid for a wider region. So he came up with an idea that, well, so what happens, even if some small scale eddies penetrate inside the flame, wait a minute, asymptotic theory tells me the reaction layer is much thinner by a factor of 10. So I still have a room for having small eddies up to this big. It'll shred my preheat zone. It'll affect the transport there, but it's still big enough to penetrate into the reaction zone. The scale ratio between the two, there's a factor of 10, given by the Zeldovich number. I hope you guys remember the definition of that. So that is a reaction layer-based, reaction time-based Karlovitz number, which has about factor of 100. Remember, there's a square factor in terms of length scale ratio. So between regular Karlovitz to reactive Karlovitz number, there is about order of 100, 2 orders of magnitude gap. So basically, it's a justification that even more intense turbulence, laminar flame assumption is valid. So we really care about that because we know what happens in laminar flame. I'm just trying to make an excuse to use my laminar flame knowledge into turbulent combustion exercise. That's essentially the game we're playing. So there goes the famous Borghi diagram. So this one is, again, we are trying to span the turbulence scenario based on 2 non-dimensional number. One is a length scale ratio. This is a turbulent integral, large scale integral eddy normalized by flame thickness. And this is a velocity scale ratio. And you can, I skipped all these algebra part. You can do all this math and figure out where those iso lines of Karlovitz, Damkohler, Reynolds falls in, which is kind of drawn here. So Karlovitz number 1, Reynolds number, first of all, is here. Reynolds number 1 falls here. Reynolds number less than 1 is laminar flame. As Reynolds number increases, you're going this way, intense turbulence. Karlovitz number unity, which is a Klimov-Williams criterion, is here. As Karlovitz number increases, you go up this way. So this is 1 and 100. So below that is a laminar flame net regime, according to Williams. And between this and that, this band is called, originally thought to be distributed combustion. Now Peters argues, well, it's still more flame-like. We call it reaction sheet regime. And beyond that, then even small-scale eddies start to penetrate, shred the reaction layer, and then you can't call it flame anymore. And Damkohler number is also important. Damkohler number goes that way. So this is a majority of the combustion community is using this, and every time you want to investigate turbulent combustion device, you try to estimate this typical velocity scale, length scale, try to pick your point. My operating condition falls somewhere around laminar flame net regime or reaction sheet regime, and so on. So we know what to do in terms of modeling. I don't like Borghi diagram, but again, I'm just a minority. I cannot go against it. My criticisms are these both axes are length scale of the integral scale eddy. Integral scale eddy length scale depends on the system size. So by inherently, these axes are system-dependent quantities, and I don't like that. I like more universal definition of non-dimensional number, which is the whole purpose of non-dimensional parameter. And furthermore, flame speed, LF, flame thickness, this is a property of the premixed flame. So this diagram is only valid for premixed combustion. I can't do anything about non-premixed combustion. And finally, actually, this can create some confusion for some even experienced researchers. Look where the Karlovitz direction is going. It's going that way. The large Karlovitz number means that the smaller eddies are getting smaller and smaller and shred the flame structure. So that's happening this way. But when you associate high turbulence, you go by Reynolds number. So high Reynolds number direction goes that way. Right? So this is a high Karlovitz corner, high Reynolds corner. So, well, so what is happening? What happens when the turbulence increases? Well, so should I be on here or there? It looks as if these two limits are separate. And this is actually a mistake. You know, when you span the world map, from the actually world map is globe, if you expand it on the plane, your North Pole becomes gigantic. Right? That's what happens here. Actually, these 2 points are not reached independently. It is going in the right direction consistently. So what I propose, again, I know you're not going to listen anyway, but I'm still saying it anyway, is Williams came up with this idea actually before Borghi. It was available way back in 1970s. Is the Reynolds Damkohler axis. You know, it makes a whole lot of sense to me because Reynolds number is the direction of turbulence intensity. Damkohler number direction is chemical intensity, universal. It doesn't matter whether it's premixed, non-premixed, it's universal. And then again, you can do the scaling argument of Karlovitz number. Isoline of the Reynolds number is obvious. So this is so the Reynolds number 1 is laminar, so which is kind of hidden here. So same. This time, actually, this end is a wrinkled laminar flame regime is infinite Damkohler number regime. High Reynolds number, turbulent is on that corner. And then Damkohler number shrinks. And this is a Klimov-Williams. So this is a increase of the turbulence, and then you are starting from wrinkled and strongly corrugated. This is a band that Peters talked about. So reaction sheet reaches out up to here. And anything below Damkohler number of 1, that's when even the largest integral scale eddy penetrates inside the flame thickness, and you are shredding everything. So it's corresponds to distributed combustion. So, in my opinion, the Reynolds Damkohler number is a really nice representation of our combustion and turbulence characteristics, and I think we should use that as an independent axis. And back to the point of my third point here, on this axis, the high Reynolds and high Karlovitz number, where is the Karlovitz number direction? Increasing Karlovitz number goes that way, Reynolds number goes that way. So high Reynolds Karlovitz number is approached at the same lower right corner, which is how it should be. You can't just simply increase Reynolds number without Karlovitz number. It depends on how you raise Reynolds number. Typical way of doing it is you are not changing the box size, right? You are stirring faster. So integral scale is fixed, and small scale gets smaller and smaller. And that axis is exactly coincident with increasing Karlovitz number axis. So I think this figure makes a whole lot more sense. And I would like to propose, whoever learned from my lecture, start using Williams diagram. I'm not paid by Foreman Williams, but I try to advertise it. Yeah, sure. Well, it's not a big a deal. And even I communicate with Foreman Williams about that. He thanked me, but he said, it's not a big deal as long as, so, but anyway, I have a rather strong opinion on that. So this is what happens, just to visualize what happens between, and so in terms of actual, this goes back to my earlier discussion of flame instability. The main microstructure of the flame, premixed flame we are talking about, depends a lot on whatever the small scale eddies do, which is a Karlovitz number effect. So that's why people are talking about, when we talk about extreme turbulent combustion, it's a Karlovitz number that people pay attention to. So large Karlovitz number, which is a small Kolmogorov-Damkohler number, that's the way I like to use it, but anyway, that's how people use it, is this. So this is a DNS simulation of the premixed flame propagating in a channel, hydrogen flame. The yellow and red isosurface indicate progress variable, upstream and downstream boundary. You see Karlovitz number small. Again, the action of eddies are mainly wrinkling the flame front without affecting the laminar structure. As the Karlovitz number increases more and more beyond 10 and even hundreds, and then you see clearly its flame structure is heavily modified. So we can't honestly call this to be a laminar flames. So the question is, though, is that relevant in practical system? And this is a kind of a mainstream research subject of the combustion group in working on turbulent combustion. You might, some of your CCRC people may have seen Professor Driscoll's invited talk at the conference a few weeks ago. There are a few groups of people in the world trying to push the Karlovitz number in the burners, in the premixed combustion burner in the laboratory, try to reach, well, numerics, it's relatively easier. I just spin the heck out of it and increase the turbulence is fed inside this inflow, which can be forced further or you can let it decay. Either way, you can increase the intensity of turbulence. You can make this happen more easily. In laboratory, it's a lot harder. So the Professor Driscoll, so far, he has been reporting that it's going to be terribly difficult to reach that condition. So it's probably not all that important. So jury is still out there. We don't know. This is another research subject to investigate. Although one thing we can say is a relative thing. Length scale, you can decrease the length scale of eddies, or you can increase the flame thickness. When can you broaden the flame thickness? How can you do it? Anyone? Anybody? How can you have a flame thickness bigger? Give me an example. Lower pressure, okay. That's why? Because flame thickness is a function of diffusivity. Then diffusivity gets larger, and you have a spread. I can't hear you. Fuel property, yeah, but again, I picked up fuel. That's a good point, but if I picked up fuel, I want to burn methane in a natural gas burner. How can we reach that condition of broadened thickness? Yes?
Choosing conditions where the thermal diffusivity is high,
yep,
and the burning velocity is low.
That's a perfect answer. So that's exactly how my student would respond. You look at the scale. This is why I emphasize a whole lot about this scaling and scaling and scaling, because if you go back to the fundamentals, you know what to do. Flame thickness delta is nu over SL. So you either increase nu or decrease SL. That's the answer. And one example is how about preheating upstream temperature? And then, yeah, that's another way of doing it. Diffusivity grows a lot, right? So think mild combustion. So actually, mild combustion is a very popular topic today in turbulent, in the practical application. By the way, mild is an acronym in case you didn't know. It doesn't mean combustion happens mildly, although it does, but it is an acronym. It's like a medium to intense, moderate to, low dilution. Yeah, thank you. Anyway, so mild combustion is one area that are of practical interest. I'm jumping ahead. And that's the region where we suspect that this kind of flame pictures are relevant. And I'll just leave it at that. So if you are wondering why do we care about all this, there is some practical context. Okay, so that was about premixed combustion. What do we do with non-premixed? Now I bragged about the beauty of Williams diagram. I think I can do a little bit on that and try to come up with regime diagram for non-premixed combustion, although it really doesn't make a whole lot of significance compared to premixed counterpart. Just let me try to point out, this is what I try to do based on, this was what made into Ed Law's book. Main difference is now you need to realize in the main unique feature of non-premixed flame is that the chemical time scale and transport time scale are decoupled in non-premixed flame. That's another important thing to remember. In premixed flame, they are always coupled. If you have rapid mixing, you have to burn faster and so on. So you have to adjust those time scale, always 1-to-1. Non-premixed flame, I told you, infinite reaction rate is fine, perfectly fine. So you can't do that. The flame time, there's some decoupling. So I'm realizing that I'm spending a little too much time here, so I will just try to skip through it. But basically, transport zone thickness, which is based on mixture fraction, will tell us about roughly the thickness. Again, this is an estimation of the flame thickness, which is a transport zone of the non-premixed flame. That has nothing to do with chemistry. On the other hand, chemistry timescale is still there, and that should be based on the Damkohler number. So we have two different Reynolds Damkohler diagrams still can be drawn like that. So infinite Damkohler number is possible. The Reynolds number going that way, this is laminar flame. The main idea here is a Damkohler number based on Karlovitz, where the Karlovitz Damkohler number reaches 1. That means, once again, we're now talking about Karlovitz eddy, smallest eddies, penetrating inside the transport layer of the diffusion flame, which is governed by the strain rate, not by the reaction, all right? And that's when you can start thinking about local quenching. Indeed, it is a Damkohler number of 1 that is the onset of extinction near the turning point. So between here and there, this is a thin reaction zone. There's no such a thing as the laminar flame. This thin reaction zone literally means the laminar flames, non-premixed version. And you are starting to see some broken holes once your Damkohler number Karlovitz start to drop below 1, and then you can have a complete shredded combustion. So this is my way of interpreting non-premixed combustion regime diagram, but it's, again, not all that important. There is an earlier Cohen-Poinsot version, which I don't like, but I'm just still citing it because it has been published. The reason why I don't like is, again, it is based on system-dependent length scale ratio. They have defined vortex Reynolds number and so on, and they came up with a similar diagram. Of course, they did it earlier, so I followed them. So that's the kind of a discussion about non-premixed combustion. So much for the regime diagram. I got 30 minutes left. I need to speed up. Now let's talk about 3 different legs about turbulent combustion simulation: DNS, LES, and RANS. And I'm doing all of that in my laboratory thanks to my brilliant research members. I will talk about one by one. So basic understanding is DNS resolves everything, all the way down to Kolmogorov scale. And indeed, as you recall, the Klimov-Williams criterion, Flamelet regime, actually it's a flame thickness that is smallest, even compared to Kolmogorov eddy size. So actually your resolution requirement is even more. But we still want to resolve everything, and so there's no modeling issues anymore. All you need to pay attention to is make sure your solution is accurate, it's not swamped over by numerical dissipation and so on. So it is usually the highest cost simulation. The typical landmark DNS simulation today, combustion, usually eats up good 10 million to 100 million hours on the supercomputers. So it's a little bit crazy. RANS is a more traditional engineering approach. It runs on the statistical average concept, and it is a low cost, lower fidelity, and I will distinguish between LES and RANS in a moment. So there are a lot of traditional modeling issues. Large eddy simulations, there is some good compromise in between. Cost-wise, it's in between, and fidelity-wise, it's also in between. So that's what we're targeting for. So let me start with the DNS. DNS principle is, once again, as far as we're in the continuum regime, we resolve everything. And so roles of DNS is, and it is limited because of that. You are only limited to typical standard configuration, rectangular box. It's not even easy to have anything like a cylindrical coordinate is even challenged, but people do that. So it is highly limited, but still the role of that is because everything is resolved, as long as the solutions equations are accurate, we are supposed to produce all spatially and temporally accurate results. That can be valuable by itself as a science study. How do I understand interaction between Kolmogorov eddy with the flame thickness, like I showed you earlier? And also another important role is that now you have DNS data, you can filter and average them to test your RANS LES submodels. So that's the kind of main premise of DNS. So here's a computational demand. Again, because of, this is related to my earlier discussion. Even in the non-reacting turbulent, we want to capture large-scale motion. At the same time, we want to resolve small-scale eddies. So the higher the Reynolds number, the scale disparity gets bigger and bigger. So the computational cost goes directly with that. And if you are doing 3D simulation, this is a power law. It's crazy. So it's almost like cubic dependence. So Reynolds number increased by an order of magnitude. Your computational demand goes up by 1,000-fold. So you can realize quickly you run out of computational resources. Turbulent combustion makes it even worse because there's extra Damkohler factor, and that Damkohler number is usually large, so you have to resolve even more. So just to try to impress you with that DNS of turbulent combustion is really hard. So having said that, it's being done, even in the detailed chemistry context. So these are the two pillars of the current combustion DNS. One is compressible, the other is called Low Mach. These are the common names of the code, including mine is KAUST. The main difference between the two is the fact that the incompressible flow formulation decouples the thermodynamics. Let me ask you one question. How can you assume incompressible flow when density changes from upstream to downstream of the flame by a factor of 7, 8? What is the definition of incompressible flow? Anyone? Could you? Okay, he gives you all the right answers. Very good. So don't be confused. In case you're wondering, it's a trick question. Incompressible flow doesn't mean constant density. It's a wrong answer. If that is the case, how can we possibly do incompressible simulation for air, which density can change a lot? It is all about Mach number, and again, unfortunately, I don't have enough time to talk about that. That way, the pressure is decoupled between thermodynamic to hydrodynamic component, and it is only the hydrodynamic component of the pressure, which is order of Mach number square, small variation. That is the only one that we keep. And that is the one that's driving the flow field of the subsonic flow field. And that pressure needs to be determined now that we decouple density from there. So we decouple it and solving by a steady Poisson equation. So the main point is the computation. This is a very, very important point from CFD point of view. Compressible flow is very straightforward, numerical algorithm-wise, because it's a method of lines. It's a system of ODEs for all the variables. You set up initial condition, you march in time. That's it. Low Mach is tricky. You thought you eliminated this compressibility effect, but you have to solve for this. There's no partial T term, so you have to solve for this algebraic constraint equation, which requires iterative solution. So this Poisson solver needs to be embedded, and that is indeed usually occupies almost half the CPU time. Why are we still doing it? What's the advantage of Low Mach despite this complexity? Anyone? Because we eliminated acoustic time scale from the equation. So time step for compressible flow field must be dictated by acoustic time scale, which is too fast compared to Low Mach. I'm not interested in acoustics. I'm only interested in subsonic time scale, which is much orders of magnitude longer. So the Low Mach, even if it costs a lot more per unit delta T, but this delta T is 10 times bigger than compressible counterpart. So that's the advantage. So this is a constant debate. I mean, it's never going to be resolved. So there are groups of people in combustion community doing compressible way, including myself. There are other groups who are doing fine with low Mach. I am still personally trying to argue that now in mainstream DNS are dealing with all the detailed chemistry. The chemical time scale is the almost equal or faster than acoustic time scale. So to me, it doesn't seem to make a whole lot of sense to go with low Mach when you have to deal with detailed chemistry. So here are some examples of a DNS demonstration. Some of them are done at Sandia Lab, Sandia S3D, Jackie Chan, one of the biggest names in DNS, and John Bell Group in Lawrence, Berkeley. And this is another Jackie Chan. Our former colleague Fabrizio Bisetti did the NGA code, which is a Stanford originated code. Some of them are mine. So I don't have time to talk much about science findings out of DNS, unfortunately. I'll skip through that. I'll stick with the computational aspect. Here's some important discussion I would like to make. So the more and more people want to run real chemistry simulation for real fuel. I mean, it's not methane anymore. We're talking about gasoline, PRF. This is a famous Liu law diagram about how much we have gone crazy about detailed chemistry. Number of species has grown up to here. This is already almost decade-old diagrams. There must be a few more, including some of the largest mechanism that I got from Mani was like that. Probably he has bigger one now. There seems to be, for some reason, approximately the linear relation between number of reactions with number of species, about factor of 5. So that's how it grows. So larger species, number of species, you have larger number of reactions. Well, so each of these reactions deal with different time scales. How is that time scale determined? Well, in a simple Chemkin format, activation energy, pre-exponential factor A, E, alpha, those are the rate constants. If you plug in, then you know the rate. And that is actually determining the chemical time scale. So it's, again, just as there's a huge spectrum of time scale in turbulence, in the chemistry, it's even more. So you have to deal with that. So this is a common terminology we call stiffness. All right, so here's some argument I would like to make. So can somebody define what the definition of stiffness? What is it? Go back to the same person. What is the stiffness?
There's somebody way over there. Oh, I see you.
Yeah, throw. Oh. Give me your definition of stiffness, numerical stiffness.
Eager to hear.
Numerical stiffness happens when a quantity changes over a very small scale of time.
Mm-hmm. Well,
that's happened in boundary layers.
Okay. Why is it small? Small is always relative sense compared to what?
I don't know exactly.
So, well, if it's nanosecond, is it small? If it's a microsecond, is it small?
Should depend on the system.
Depend, exactly, right?
Yeah.
So could you throw them back? This is an important concept I would like to make point out of. That's why I'm taking some time here.
Okay, so there could be two aspects to it. One is the number of known variables is less than, number of known equations to solve is less than the number of unknown variables. Or the second part could be that there are variable time scales or scales which need to be solved. So the way the solution goes, it's quite different. So it's hard to make out in which direction the solution is marching.
Okay, I'm not sure if well, anyway, let me get to the point. So stiffness is usually defined as the time scale disparity, just the way we define spatial scale disparity by Reynolds number. So I have hundreds of chemical reacting species with thousands of reactions. Each of them has different time scales. Some of them are order of seconds, others are order of nanoseconds. Maybe, hopefully not femtosecond, which violates molecular kinetics. But then again, I have another integral time scale that I need to resolve to describe turbulent combustion system. So it is the ratio between long to small time scale. That is, the bigger that is the stiffness. But wait a minute, is that, why do we have nanoscale, for example? Do I need that? That is a point I'm trying to make. So here's my practical definition of stiffness. An initial value problem is stiff if delta t needed to maintain stability of explicit timescale. You see the explicit timescale CFL number. Reactive, you need to take the delta t small enough to ensure numerical stability of the solution. So keep in mind, stability is not the same as accuracy. Accuracy means I'm describing the right physics with the fidelity. So there is a separate requirement to maintain accuracy of the solution. For example, ignition time, delay time, I need to capture that. I need to predict the pollutant formation. So there is an extra delta T required for ensure accurate solution. Only you can know as a scientist whether it's accurate or not. Delta T for stability, your code will tell you, otherwise it'll blow up. So if delta T needed to maintain stability is much smaller than what I need for science investigation, that's the stiffness problem. Otherwise, it is wrong to call the problem stiff. It is not stiff. It is the time scale you need to resolve to ensure your accurate solution. Many people get confused about that. Just because you have huge dynamic range doesn't mean it's stiff system. It's just a computationally demanding problem. But it's not stiff. The nanoscale has to be resolved if that is important for your physics. Right? So the ultimate question you have to ask yourself, are there small time scales relevant to your physical dynamics? Ignition, extinction, whatever. If it matters, then you have to keep it. If it's not, forget it. How do I know? Well, there are ways to figure that out. And you can either do it by trial and error, but by getting rid of it, see if it makes a difference in terms of quantity you want to explore, and so on. So if the answer to that question is yes, then even if you have 10 decades of time scale difference, doesn't matter. You have to keep them. And if you want to keep them, explicit time integration is the easiest way to do it. If it's no, then it's a stiff problem in my definition. Then there are some unnecessarily fast time scale that I don't need in dealing with my physical problem. So then I have to do carefully to check the dependence and try to get rid of those time scale. So that's one way I would like to deal with it. Otherwise, well, if it's stiff, there's another solution, which is called implicit time integration. Those who have done CFD knows implicit time integration is unconditionally stable. So it'll give you a solution no matter what delta t you take. So you take 10 seconds of delta t from now, you will get a solution, except it's going to be completely meaningless. So there you go. So one remedy of stiff problem is you keep the stiffness and use implicit solver. In my opinion, it's a lazy approach. Probably a smarter approach is, well, I'll do a more rigorous analysis and remove those stiffness. Then I know absolutely make sure those important time scales are all kept. Then I'll have to do high fidelity time integration. In doing that, I don't need implicit time integration. That's my message. So here is my response to our Professor Mani Sarati. He's been using this. He's so passionate about chemistry development. He thinks of it as an art of designing detailed chemistry. It's beautiful. All the fine scale details of these complexion, lips, it's a work of art. And then we CFD guys just completely destroyed by doing a skeletal mechanism. All right, so that he was upset about that. Well, what I would like to argue is if you do it carefully, then you can still preserve essential beauty without making this skull. So that's my view of reduction. You can change the brush stroke and create another equally artistic image without too much details. So that's what I'm trying to talk about. In my opinion, there's a lot of this common misconception about these stiffness issues. And people try to throw everything in and just hoping to see, why do you do that? I mean, why do you need all this fast time scale if you don't need it? So do it carefully beforehand and remove them. Once you remove them, I don't need implicit time integrator. So that's my vision of high fidelity DNS. And this computational singular perturbation that I have had the privilege to work with my longtime colleague Mauro Valorani at University of Rome, it allows me to do that in a systematic way. And what it does is, simply put, it's a kind of eigenvalue decomposition because everything is coupled together. You map it into the eigenspace to decouple total n characteristic time scale. Some of them are fast and some of them are slow. And it allows us to distinguish fast and slow modes. Here, fast means unnecessarily fast. So those are called exhausted mode. So those are so fast, I don't care. So that's the one I can safely ignore. And all I need to keep is a slower mode. And among them, M+1, that is the fastest of the active slow mode. That's what I'm most interested in. And that's my minimum time scale, time step requirement. So that's, and so I'm kind of getting nervous about that. So in the interest of time, so additional, more advanced concept of tangential stretching rate allows us to investigate these explosive diagnostics, such as ignition kind of phenomena. And all these methods combined together, it allows us to develop the skeletal mechanism. I shouldn't say skeletal anymore. It's a reduced mechanism. It's beautiful. Without having to solve all these algebraic steady-state approximation. I have no time to talk about that, but steady-state approximation, eliminates a lot of species concentration, replace it by algebraic equation. And that whatever nonlinear algebraic equation you have to iteratively solve it, which is time-consuming. So I don't want that. I'd like to just keep all the important time steps, time scales, and then do it explicitly. And the minimum accurate reaction mechanism can be done through these combinations of CSP, TSR. So we have recently developed, with the lead of the Rome group, we have demonstrated this such reduced mechanism can be developed automatically without user intuition. And this is actually an exciting tool that we will explore more in the future. And so here's one example of the KAUST Aramco PHA Mach that has been demonstrated to show a lot of useful skeletal mechanisms. Once you got that, well, still it's a quite demanding computational task, and there's a lot of these high-performance computing aspects come into play in DNS. So I have the KAUST project, KAUST Adaptive Reacting Flow Solver. Here, the word adaptive refers to the computational framework. We have GPU and CPU hybrid architecture. GPU basically means you have tiny chips, like thousands of chips in one card, and you can do a lot of simple number crunching very, very fast. So this is an optimal situation with our chemical reacting flow, where reaction source terms are local. You don't need to associate with the neighboring points. So you can do the number crunching with the GPU. So it's explicit, really fast, and then combined with CPU who can do the domain decomposition. So that's my vision. I'm not the only one working on that. Sandia group is also doing that. There are a few other groups. This is a new computational aspects of the research task facing these DNS. So we have worked with Ramanan Sankaran at the Oak Ridge National Lab to improve those. And this is, again, then the machine-dependent programming is crazy. So we want to wrap around with this KAUST framework, which is developed at Sandia Group, and that allows the user to freely choose between how many number of CPU to GPU combination you can utilize. So this is a kind of a future direction of high-fidelity simulation, especially in DNS approach. We have made some initial validation of how much speed up we can achieve, and I'm not going to dwell on the numbers. So how are you doing? 10 minutes left for the 5, okay? So I can possibly combine RANS and LES in 5 minutes. I was going to throw some questions about it, but so main distinction between RANS and LES is the Reynolds averaging versus spatial filtering. Again, there's one common misconception about many students from my class. They always say, what is Reynolds averaging? And they say time averaging. It's wrong. Reynolds averaging is ensemble averaging, which means sample-to-sample averaging. The very good everyday example is IC engines. So imagine you're doing time averaging of IC engine information. It'll be flat, right? Doesn't make sense. But if you have phase-locked information about every 10 the top dead center information, it'll be fluctuating, but you can get the average quantity. That's Reynolds averaging. That's what we call ensemble average. We run many different realization and average over. That's what's shown here. Of course, that ensemble averaging becomes time averaging under special condition, which is happening when actual time averaging, the statistical average quantity doesn't change over time. So for example, in this is a comparison of the jet flame. Of course, it's not exactly the same condition, but this is more like a detailed DNS. And that's LES, which is kind of filtered, smeared image. It's like a low pixel image. RANS is a temporal average of that. You have a long exposure of that picture. This is what it looks like, right? Here, RANS can be justifiably done in a time average manner because statistically it doesn't make a difference whether I take the snapshot now or 10 seconds later, okay? But if the mean ever changes over time, you can't do the time averaging. Okay, so one more point I would like to point out here. So now, skipping all the details, LES is spatially filtered, RANS is Reynolds averaged. But after that, you derive the equation. And this is what you come up with in a non-reactive manner. So you have the expression of the equation is exactly the same, except some minor details about these stress terms, tau ij. This is our LES version, and RANS. Of course, the details of that also depends on specific model that you choose. So we call it Reynolds stress. We call that as a Lennard subgrid stress. So from a coding point of view, well, it's a piece of cake. I get the fluent code, RANS version. I modify a few lines if you have access to source code. Change a few lines, I'm done. I have LES code. Great. You have to be careful about that. So why do we not do that? Well, some people actually do, indeed. And this is some message I took from the brilliant lecture note by Thierry Poinceau. He makes great lecture notes. I really liked his lecture notes. So here's a point we are trying to make. This is basically the viewpoint of a Stanford group, which I'm also from. And Parviz will really scream when we talk about those high order low order dissipative scheme in LES. Here's the reason why. So every turbulent flow field, there's a laminar viscosity. And turbulent viscosity, which is actually like an action of eddies, but we call it the viscosity because we model that way. It is a kind of turbulent action banging onto each other that smears out things. And then there's always a numerical dissipation. In the RANS simulation, usually scales are big, and turbulence dissipation dictates everything. So if this is 100, even if my numerical viscosity is 10, it's all right. So I can easily use a lot of these low-order methods to do RANS perfectly. And the results will not change much. But when you want to use the same code with the LES, then we're talking about much higher resolution, and subgrid kinetic energy part, which contributes to this turbulent viscosity component, is not a lot. So we are reducing this from 100 to 10. Now, if this was 10, now I have to worry. So that's the main point I would like you to carry on. So be careful. When you want to convert, algorithm is the same. My point is that you need to improve your accuracy of your code, the schemes. Spatial discretization, time integration, you want to improve them in order to ensure your good LES. Otherwise, you get the LES WE, according to Poangso, which means large eddy simulation without eddy. So I think I'm pressured to close the... There are standard discussion about turbulence combustion submodels, but without having to take Bank's time and without breaking into your lunch time, I will leave it there. But these are all standard textbook material you can find. And yeah, I have examples of LES and DNS, the RANS simulation. Well, I didn't expect I'll run out so much time, but this is my mistake. But I apologize. The rest of the material is available, will be posted on the lecture notes. I'll be happy to engage with your further questions. Okay? So thank you all. So I'll take any more questions.